Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route through the dark. Tonight we are drifting toward one of the strangest kinds of explosions astronomers have ever seen, a class of cosmic flashes called Fast Blue Optical Transients, or FBOTs, which is a tidy little name for something that is not tidy at all. These are explosions that appear suddenly, shine with a hot blue glare, brighten with shocking speed, and then fade away before scientists have had a proper chance to lean closer and say, "Excuse me, what exactly were you?" In a universe full of dramatic objects, exploding stars, collapsing cores, hungry black holes, and galaxies slowly pulling at one another like sleepy giants, FBOTs still manage to feel unusually rude. They arrive without warning, put on a brilliant display, refuse to explain themselves, and then leave the room. Maybe that is why they're so fascinating. Space is full of mysteries that last billions of years. Some questions move slowly. How do galaxies grow? What is dark matter? Why is the universe expanding faster than expected? These are the long, quiet puzzles, the kind that sit with scientists for generations. But FBOTs are different. They are quick puzzles. They are cosmic interruptions. They are the sudden blue flash in the corner of the telescope's eye, the thing that appears overnight and says, "You have about 3 days to understand me, good luck." And if that sounds a little unfair, well, astronomy has never promised to be convenient. The universe is beautiful, but it is not always considerate with scheduling. So before we follow this blue trail into the deep sky, let me ask you gently, where are you listening from tonight? Are you somewhere quiet, with a lamp glowing nearby? Maybe the day finally slowing down around you? Or are you listening from a different hour entirely, morning for you while it is night for someone else, your little place on Earth turning beneath the same sky that once carried the light from these strange distant blasts? If you feel like it, you can leave your corner of the world in the comments and maybe tell me what the sky is doing where you are. Clear, cloudy, rainy, moonlit, city bright, or so dark that the stars look like tiny pinholes in a great black curtain. There is something comforting about remembering that we all look up from different places, and yet the same universe stretches above us, quietly full of things that have not introduced themselves properly. And if you find this kind of slow science soothing, if the strange behaviour of faraway explosions somehow helps the busy part of your mind settle down, I would be very grateful if you liked the video and subscribed. It helps this calm little corner of space reach other curious people who might also enjoy learning about the universe at a pace that does not hurry them toward the next alarm, the next message, or the next cup of tea. Though to be fair, if you already have tea, you are scientifically ahead of the curve. Now, settle in, let your thoughts loosen a little, and we'll begin with a flash of blue light so brief, so bright and so confusing that astronomers are still trying to decide what kind of cosmic event they actually witnessed. A fast blue optical transient sounds, at first, like a description rather than a name, because that is exactly what it is. Fast, because it rises and fades much more quickly than an ordinary supernova. Blue, because the light is extremely hot, so hot that its glow is shifted toward the blue and ultraviolet part of the spectrum. Optical, because we first notice it in visible light, the kind telescopes can catch as a sudden new point in the sky. Transient, because it does not stay. It is here for a little while, then it weakens, dims, changes, and eventually blends back into the background, leaving behind data, arguments, and several astronomers who probably did not get enough sleep that week. That name tells us what FBOTs look like. It does not tell us what they are, and that is the important difference. In astronomy, sometimes a name is a diagnosis. A white dwarf is a small, dense stellar remnant. A red giant is an old, swollen star. A neutron star is made mostly of neutrons, which is both impressive and deeply unhelpful if you were hoping it might be soft and friendly. But FBOT is not that kind of name. It is a label placed on behaviour. It is astronomers saying, "This thing got bright very quickly, it was blue, it faded quickly, and we do not yet agree on what physical engine made it happen." It is less like naming an animal, and more like saying, "Something large just ran past the window." For a long time, when astronomers saw a bright new point of light in another galaxy, one of the first suspects was a supernova. That makes sense. Supernovae are among the universe's most powerful explosions. A massive star can run out of fuel, lose the pressure that once held gravity back, and collapse in on itself before blasting its outer layers into space. Or, in another kind of supernova, a white dwarf can gather too much material and ignite in a runaway thermonuclear explosion. Either way, the result is enormous. For days or weeks, a single dying star can shine with the power of billions of suns. It is one of the great dramatic exits in nature, though admittedly a little more intense than quietly leaving a party after saying goodbye to the cat. But supernovae usually follow certain patterns. They brighten over days or weeks. They fade over weeks or months. Their colours, spectra, and chemical signatures can often tell astronomers what kind of star died, what material was thrown outward, and what process powered the glow. There is still plenty to learn about supernovae, of course. Scientists do not look at an exploding star and shrug as if it is yesterday's laundry. But compared with FBOTs, supernovae are at least more familiar. They have a recognisable rhythm. FBOTs arrive as if someone has taken that rhythm and pressed fast forward. A typical luminous FBOT can become bright in only a few days. Its blue light suggests very high temperatures, sometimes tens of thousands of degrees. Its brightness can rival or exceed many known stellar explosions. Then, instead of lingering in the way many supernovae do, it fades rapidly. That fast rise and quick decline are not small details. They are clues. They tell astronomers that the emitting region may be compact, that energy is being released or exposed very quickly, and that the usual explanations involving large amounts of radioactive material may not be enough. If a normal supernova is like a bonfire that grows, burns, and slowly settles into embers, an FBOT is more like opening a furnace door in the dark, getting blasted by sudden blue-white heat, and then watching the door slam shut again. The first famous member of this family, the one that pulled FBOTs into the wider scientific spotlight, appeared in 2018. It was given the official name AT2018 Cow. The last three letters, Cow, came from an automatic naming system, not from someone deciding that the universe needed more farm animals, although astronomy has cheerfully leaned into it ever since. This object became known simply as the Cow, and as you can imagine, once astronomers have a cosmic explosion called the Cow, the jokes become almost impossible to resist. But the event itself was no joke. It appeared in or near a galaxy about 200 million light-years away, brightened with astonishing speed, and immediately stood out as something strange. Think about that distance for a moment. 200 million light-years. The light from the Cow began its journey toward us when Earth was a very different place. Long before humans, long before cities, long before anyone had ever looked up and wondered what a transient survey was. For all that time, those photons crossed the dark between galaxies, passing through space almost entirely unnoticed, until finally they reached a telescope built by a species that had recently invented both astrophysics and the snooze button. And when the light arrived, it did not announce itself gently. It appeared as a new bright point where there had not been one before, and because modern telescopes scan the sky again and again, comparing tonight with last night, the change was caught quickly. This is one of the reasons FBOTs belong so strongly to the age of sky surveys. In the past, many fast events would have been missed. The sky is enormous, and most things in it do not change much from one human night to the next. Stars sit in their patterns. Galaxies keep their soft, smudged shapes. The moon wanders through its phases and behaves more or less like the moon. But fast transients require patience, repetition, and wide eyes. You have to look at the same patches of sky over and over, not because you expect everything to change, but because once in a while, something does. Automated surveys do this work with tireless attention. They take images, compare them, flag new objects, and send alerts so astronomers around the world can turn larger telescopes toward whatever just happened. It is a little like having a night watchman for the universe, except the night watchman is made of software and has no interest in biscuits. When AT2018 Cow was detected, follow-up observations began quickly across many wavelengths. That matters because visible light is only one piece of the story. An explosion can glow in optical light, ultraviolet light, X-rays, radio waves, and other parts of the electromagnetic spectrum. Each wavelength gives a different clue. Optical light may tell us how hot and bright the visible material is. Spectra can reveal chemical elements and motion. X-rays can point toward very energetic processes near compact objects, such as black holes or neutron stars. Radio waves can reveal shocks crashing through surrounding gas. To understand a strange explosion, astronomers do not simply look once and say, "Well, that was blue." They gather light in as many forms as possible, because the universe often hides the answer in the part of the spectrum you were not planning to check, and the cow was noisy. Not noisy in sound, of course, because space does not carry sound through its emptiness the way air does in your room, but noisy in information. It produced bright optical light, strong ultraviolet emission, variable X-rays, and radio signals that suggested fast material ploughing into surrounding gas. It looked too bright, too hot, too fast and too active to sit comfortably inside the usual supernova boxes. Scientists began asking whether they were seeing a star explode while something powerful remained alive in the center. Maybe a newborn black hole was feeding on fallback material. Maybe a newly formed neutron star or magnetar was injecting energy into the debris. Maybe a star had been torn apart by a compact object. Maybe the event was a strange kind of stellar death, involving dense material already surrounding the star before it exploded. Each idea explained some clues and struggled with others, which is a polite scientific way of saying that nobody could quite get the whole thing to behave. This is where FBOTs become especially interesting. They may not simply be odd supernovae, they may be windows into a short hidden stage that ordinary observations usually miss. In many stellar explosions, the central engine, if there is one, is buried beneath thick layers of debris. Light diffuses outward slowly. By the time we see the event clearly, the earliest and most violent inner details may already be blurred. But FBOTs evolve so quickly that they may allow astronomers to glimpse energy escaping from deep inside the explosion almost in real time. It is as if nature briefly lifts the lid on a stellar catastrophe before closing it again. For scientists, that is thrilling. For the star, presumably less so. The blue colour is another important clue. Blue light means heat. In everyday life, we often associate red with hot and blue with cold, because taps have trained us poorly. But in physics, blue hot is hotter than red hot. A red ember is warm compared with the room, but a blue-white star or a blue-white flash is far more energetic. FBOTs glow blue because the material producing the light is extremely hot in the early stages. That temperature can change rapidly as the event expands and cools, so astronomers race to capture early data. Missing the first few days of an FBOT can be like starting a mystery novel halfway through and discovering that all the best clues were in the pages someone used as coaster. There is also the question of rarity. FBOTs do not appear all the time. They are much less common than ordinary core collapse supernovae, or at least the bright cow-like versions are. That rarity makes them precious and annoying in equal measure. Precious, because each one gives scientists a new chance to test ideas. Annoying, because rare events do not politely appear when the right telescope is available, when the weather is clear, and when every astronomer has had a decent breakfast. Sometimes they appear in awkward parts of the sky. Sometimes they are discovered after the earliest rise has already passed. Sometimes they fade while people are still arguing about what observations are most urgent. The universe has never been very good at filling out scheduling forms. Since the cow, other strange members of this family have joined the list, and because astronomers are human beings with a weakness for memorable nicknames, some have been called the koala, the camel, the finch, and the Tasmanian devil. These names sound charming, almost like a children's book about animals who accidentally wandered into a telescope proposal. But behind the names are serious puzzles. Some events show powerful radio emission. Some show unusually strong X-rays, some appear in unexpected environments. Some flare again after the first explosion, as if the object is not finished speaking. The Tasmanian devil, for example, became especially puzzling because it produced repeated short optical flares long after the initial blast, suggesting that something compact and energetic may have survived at the centre. A dead star should not keep tapping on the window months later, unless there is an engine inside still doing work. That word, engine, will come back again and again. In ordinary language, an engine is something in a car, a machine that burns fuel and produces motion, while making noises that become expensive if ignored. In astrophysics, a central engine is the hidden power source that keeps feeding energy into an event after the first explosion. It might be a black hole pulling in material. It might be a spinning neutron star with an extreme magnetic field. It might be a compact object interacting with a star or its debris. The visible explosion is the display. The engine is what may be working behind the curtain. And with FBOTs, many of the clues seem to point towards some kind of compact engine. Something small, dense and intense enough to keep producing energy after the outer blast has already begun to fade. Imagine gently a massive star reaching the end of its life. For millions of years it has balanced gravity with the pressure created by nuclear fusion in its core. It has made heavier and heavier elements, layer by layer, like an onion with a very dramatic future. Eventually the balance fails, the core collapses, the outer layers are thrown outward. In a normal telling, this becomes a supernova, and depending on the details, the core may leave behind a neutron star or black hole. But now imagine that the star was surrounded by dense material it had shed shortly before death. Imagine that the core collapse created a compact object that began feeding or spinning rapidly. Imagine that energy from the centre found a way out unusually fast. The result might not look like a normal supernova. It might look faster, hotter, bluer, stranger. It might look like an FBOT. Or perhaps not. That is the honest answer, and it is part of what makes the topic so compelling. FBOTs are not solved. They sit at the edge of several explanations. Some models involve failed supernovae, where a star begins to explode but much of the material falls back onto a newly formed black hole. Some involve magnetars, young neutron stars spinning rapidly with magnetic fields so strong they make ordinary magnets look like polite suggestions. Some involve tidal disruption, where a star is torn apart by a black hole, though not necessarily the giant black holes that sit in galactic centres. Others involve unusual kinds of stellar mergers or compact companions hidden inside complicated systems. The data do not yet point to one simple answer. Instead, they point in several directions at once, which is scientifically inconvenient and very good for a sleepy mystery. In a way, FBOTs remind us that the universe is not arranged according to the categories in our textbooks. Our categories are useful. They help us think. They help us teach. They help us build surveys, compare data, and decide what telescope time to ask for. But nature does not have to respect them. A real cosmic explosion may borrow features from several boxes. It may look a little like a supernova, a little like a tidal disruption event, a little like a gamma-ray burst after someone turned the dial down, and a little like something we have not named properly yet. When scientists find an object like that, it can be frustrating, but it is also a sign that discovery is still alive. The universe is not finished surprising us. It still has events that make experts pause, squint at the data, and perhaps reach for another cup of coffee with the seriousness of someone entering negotiations. For us, listening quietly here on Earth, there is something almost gentle about studying such violent things from a distance. The explosions themselves are enormous. They involve energies that are difficult to hold in the mind, temperatures that would erase ordinary matter, speeds that push material outward at fractions of the speed of light, and compact objects so dense that our everyday intuition simply gives up and goes to bed. And yet the light reaches us softly. It arrives as numbers in a detector, as a bright pixel, as a curve on a graph. It becomes a paper, a debate, a model, a late-night observation request. The violence is real, but by the time it reaches us, it has become information. That is one of astronomy's quiet wonders. The universe can be ferocious, and still we receive it as light. The night astronomers met the cow did not begin with a person standing under the stars, pointing dramatically at the heavens and shouting for someone to fetch a notebook. It began in the modern way, with a survey telescope doing its quiet work, taking images of the sky over and over again, looking for anything that had changed since the last time it looked. Most of the time, this kind of work is patient and ordinary. A telescope looks, a computer compares, the sky mostly behaves, the same stars sit in the same places, the same galaxies appear as pale little smudges. A few known asteroids wander through the frame, like tiny nearby crumbs moving across a very large table. Then, once in a while, something new appears, and the calm routine becomes a message from deep space. On June 16th, 2018, one of those messages arrived. The Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, was scanning the sky from Hawaii. ATLAS was designed mainly to look for potentially dangerous asteroids, the kind of objects that make planetary defense people pay close attention, and everyone else quietly hope the calculations are correct. But a sky survey that watches for moving objects can also catch sudden brightening events far beyond the solar system. It can notice when a point of light appears where no point of light had been before. That is one of the useful things about watching the sky repeatedly. You may be looking for rocks near Earth, and instead you find a cosmic explosion in another galaxy. Astronomy is very good at making a neat plan, and then immediately handing you something stranger. The object was first catalogued as ATLAS 18QQN, which sounds less like a cosmic mystery and more like a password someone made while half asleep. Soon after, it received its official astronomical transient name, AT2018COW. The final three letters were not chosen as a joke. They came from the automatic naming system used for transient objects. Still, once the universe gives you an explosion called cow, there is only so much dignity the scientific community can maintain. Astronomers began calling it the cow, and from that moment, an extremely serious astrophysical event had to carry a name that sounded as if it belonged in a field, chewing grass, utterly unaware that it might be the birth of a black hole. That contrast is part of the charm. The cow was not small, it was not gentle, it was not a local little flicker. It erupted in or near a galaxy called CGCG 137-068 in the constellation Hercules, roughly 200 million light-years away from Earth. That distance means the light had been travelling toward us for about 200 million years before it reached our telescopes. When the explosion actually happened, Earth was in the age of dinosaurs. The Atlantic Ocean was still young. Flowering plants were not yet the familiar part of the world they would later become. The light crossed intergalactic space through age after age of Earth's history, and then, one June night in 2018, it finally arrived as a bright new point in a digital image. There is something humbling about that. A human notices a data alert and says, in effect, something has happened tonight. But the thing itself happened before any human had ever existed. This is one of astronomy's strange habits. It turns the past into breaking news. The universe sends old light, and we receive it fresh. We say that a star exploded, that a galaxy flared, that a black hole fed, but what we really mean is that the evidence has just reached us. The event has been over for millions of years. Perhaps the surrounding debris has cooled and spread. Perhaps the central object has changed beyond recognition, but to us the story is beginning now. At first, the cow was simply a new transient, a new source of light that had appeared suddenly. But very quickly, astronomers realized that it was not behaving like an ordinary supernova. It brightened too fast. A normal supernova can take many days or even weeks to climb toward maximum brightness. The cow rose in only a few days. It was not merely quick, it was startlingly quick. In some observations, it appeared to brighten by more than 5 magnitudes in just over 3 days, which means it became dramatically brighter in a very short time. Imagine walking past a dark house one evening, then passing again a couple of nights later, and finding the whole place lit from inside, as if someone had installed a small sunrise in the living room. You would probably stop. Astronomers stopped. The brightness was just as troubling. The cow was far more luminous than a typical supernova in visible light, in some descriptions at least 10 times brighter. It was also hot and blue, with a temperature much higher than what astronomers expected for many familiar stellar explosions at that stage. Blue, in astronomy, is rarely a calm colour. It often means heat, energy, youth, violence, or all of them at once. A red glow can be warm and fading. A blue-white glow can be fierce. The cow's blue light suggested that something extremely energetic was being exposed, released or powered in a way that ordinary models did not easily explain. The first few days after discovery became a race. This is one of the most important parts of the cow story. It was not enough to notice it. Astronomers had to move quickly. Fast transients punish hesitation. With a normal long-lasting supernova, scientists may have time to organize observations, request follow-up, compare schedules, and perhaps even sleep like reasonable people. With a fast blue optical transient, the object is changing while everyone is still reading the alert. Every hour matters. Its brightness, color, spectrum, X-rays, radio emission, and ultraviolet glow may all shift rapidly. If you miss the beginning, you cannot ask the universe to do it again, though many graduate students have probably wished they could. So telescopes around the world and in space turn toward the cow. Optical telescopes watch the visible light. Ultraviolet instruments measured the hot glow. X-ray telescopes looked for high-energy radiation from whatever violent process might be hidden inside. Radio observatories listened for the signs of fast-moving material crashing into gas around the star. This multi-wavelength follow-up is one of the reasons the cow became so important. A single colour of light can tell you something, but it can also mislead you. It is like judging an entire house by looking through one window. Open more windows, and you begin to understand the shape of the rooms, the source of the heat, the movement inside, and perhaps why someone left a suspiciously large cosmic lamp on. The cow did not make things simple. In optical light, it looked bright, hot, and fast. In X-rays, it was energetic and variable. In radio waves, it suggested that material was moving outward and interacting with the environment around it. Instead of pointing clearly to one explanation, the observation seemed to say several different things at once. That is often how a new class of object begins. Scientists do not wake up one morning with a tidy definition. They find something that refuses to fit, then they find another, then another. Eventually the mismatch itself becomes important enough to name. Before the cow, astronomers already knew about rapidly evolving luminous transients, events that rise and fall faster than normal supernovae and occupy a strange middle ground between familiar categories. But a T2018 cow was so bright, so nearby by cosmic standards, and so intensely observed that it became the example everyone remembered. It was not necessarily the first strange fast blue event ever seen, but it became the one that made the mystery hard to ignore. It was close enough to study in detail. It was bright enough to trigger attention. and it was odd enough that nearly every explanation felt slightly uncomfortable, like trying to wear a coat that almost fits but insists on pulling at the shoulders. One possible explanation was that the cow was some kind of unusual supernova. A massive star may have reached the end of its life and collapsed, leaving behind a neutron star or black hole. In many supernovae, the compact object at the centre is hidden by thick, expanding debris. The explosion throws out layers of material, and that material blocks our view of the deepest region. We see the outer blast, the heating, the radioactive decay, the expanding shell. But we do not usually get a clear early look at the engine inside. The cow seemed different. Its debris may have been unusually thin or arranged in such a way that high-energy light from the centre could escape. If so, astronomers might have been seeing, almost directly, the birth of a compact object. That idea is extraordinary if you pause with it for a moment. A black hole or neutron star is not a gentle thing. A neutron star is the crushed core of a massive star, packed into a sphere roughly the size of a city, with a density so extreme that ordinary matter has been forced into one of nature's strangest states. A black hole is even more severe, a region where gravity has curved space-time so strongly that nothing crossing the event horizon can return. Usually these objects are inferred after the fact. We see their effects, we observe old remnants, we detect X-rays from systems where they feed. But the cow raised the possibility that astronomers were watching the first moments after one of these objects formed, while the surrounding explosion was still hot and bright. Another explanation moved in a different direction. Perhaps the cow was a tidal disruption event. In this scenario, a star passes too close to a black hole and is torn apart by gravity. The side of the star nearer the black hole feels a stronger pull than the far side, stretching and shredding the star into a stream of gas. Some of that material escapes, some falls inward, heats up, and shines. Tidal disruption events are real and observed, usually around supermassive black holes in the centres of galaxies. But the cow was not sitting neatly at the centre of its host galaxy, which made the situation more complicated. Some models suggested a smaller or intermediate mass black hole ripping apart a compact star, perhaps even a white dwarf. That possibility was fascinating, but it also required special circumstances. The cow was not eager to make any explanation cheap. A third family of ideas involved a magneta, a newborn neutron star with a magnetic field so powerful it can pour energy into the surrounding debris. Magnetars are among the most magnetic objects known. Their fields are so strong that if one came too close to Earth, which thankfully is not on the evening schedule, it would cause problems for atoms, electronics, and anyone hoping for a quiet walk. A rapidly spinning newborn magnetar could act as an engine, injecting energy into the explosion and helping produce the cow's unusual brightness and evolution. This idea has been used to explain several strange luminous transients, but again, the details matter. The model has to match the light curve, the temperature, the spectra, the X-rays, the radio behaviour and the timing. In astronomy, an explanation cannot simply sound dramatic. It has to survive the data, which is much less impressed by drama than we are. One of the most curious things about the cow was how quickly it forced astronomers to coordinate. Alerts moved through networks, observatories checked visibility, teams began gathering spectra and photometry, instruments in space joined the effort. The object became a target of opportunity, one of those events that interrupts the normal observing plan, because it may not be there in the same way tomorrow. There is a human side to this that is easy to miss. Behind every smooth sentence in a paper, there are people waking up, emailing colleagues, checking weather, writing proposals, reducing data, comparing models, and realizing that the thing they are studying is changing faster than their inbox can refresh. That urgency is part of what makes transient astronomy feel alive. Some branches of astronomy study objects that change very slowly. A galaxy cluster will not rearrange itself overnight. A molecular cloud will not politely finish forming stars by the weekend. But transient astronomy lives on change. It studies things that flare, explode, collide, fade, pulse, or vanish. It turns the sky from a static map into a moving place. For centuries, people imagined the stars as fixed. The very phrase, fixed stars, comes from that old sense of permanence. But modern surveys have revealed a restless sky. Stars die. Compact objects feed. Asteroids pass. Neutron stars merge. Black holes tear things apart. And sometimes, in the middle of all that, a cow appears. The name may have helped the public notice, but the science held everyone's attention. A T2018 cow became a kind of cosmic test case. It asked whether our categories were ready for the new sky surveys were revealing. Was it a supernova? If so, why did it rise so quickly and shine so brightly? Was it a tidal disruption event? If so, where was the black hole and what kind of star was destroyed? Was it powered by a compact engine? If so, why was that engine so visible? Was the progenitor star surrounded by dense material it had thrown off before exploding? If so, what caused that mass loss? Each question opened another one. Like a drawer full of smaller drawers, none of them labelled clearly. The host galaxy mattered too. CGCG 137-068 is a star-forming galaxy, and the cow was located offset from its centre. Star-forming regions are places where massive stars can live and die. Massive stars burn through their fuel quickly, at least by stellar standards, and end their lives near the regions where they were born. That made a massive star explosion plausible. But the offset location also left room for other possibilities, including a compact system or a smaller hidden environment near the galaxy. Astronomers had to treat the setting as another clue, not a final answer. A crime scene, if we may gently borrow the phrase, tells you where something happened. It does not always tell you who did it. The early spectra added to the strangeness. Many supernovae show recognizable spectral features as expanding material absorbs and emits light at certain wavelengths. Those features can reveal elements, velocities, and the structure of the ejector. The cow's spectra were comparatively featureless at early times, another sign that it did not fit neatly into familiar supernova categories. A smooth blue continuum can tell you that something is hot, but it does not always offer the chemical fingerprint scientists want. It is like asking a witness for details and receiving the answer, "It was very bright," which is true, but not enough to solve the case. As the days passed, the cow faded, but it did not become ordinary. Its decline was fast compared with typical supernovae, and its continued high-energy behaviour suggested that something inside or around it remained active. That is why it became so closely linked with the idea of a central engine. In a simple radioactive supernova model, much of the light comes from the decay of nickel-56 and other radioactive material synthesized in the explosion. That process has a certain time scale and character, but the cow seemed too fast and too luminous for an easy radioactive explanation. The energy budget, the speed, and the multi-wavelength signals pushed researchers toward more exotic engines or unusual environments. It is useful here to imagine two clocks running at once. One clock belongs to the expanding debris. After an explosion, material flies outward, cools, thins, and changes. This affects the visible light. The other clock belongs to the hidden power source, if there is one. A compact object may accrete material, spin down, launch outflows, or create high-energy radiation. These two clocks can interact. The debris can hide or reveal the engine. The engine can heat or accelerate the debris. The surrounding gas can be struck by the outward blast and begin glowing in radio waves. In the cow, those clocks seemed unusually exposed and unusually fast, which made the whole event feel as though astronomers were watching machinery normally buried deep inside the star. That is a recurring idea in FBOTs. They may be valuable not only because they are strange, but because they are revealing. Ordinary stellar death can be wrapped in too much material for us to see the deepest process directly. FBOTs may offer a thinner curtain, not a fully open door perhaps, but a torn curtain with bright light coming through the gap. Through that gap, astronomers may glimpse how compact objects are born, how massive stars lose material before death, how jets or outflows escape, and how explosions behave when the central engine does not simply switch off. Still, it is important not to pretend that the cow solved itself. It did not. Years later, researchers were still studying it, still finding evidence that raised new questions, still testing models involving compact objects, tidal disruption, accretion, and unusual stellar collapse. That is often how real science feels. A discovery does not always arrive with a neat answer attached. Sometimes it arrives as a better question. Before the cow, astronomers could talk about fast blue transients as odd members of a broad transient zoo. After the cow, the question sharpened. What physical process can produce something this hot, this luminous, this fast and this active across so many wavelengths? There is a quiet lesson in the way the cow was found. It was not discovered because someone knew exactly where to look. It was discovered because astronomers had built systems that could notice change. That may sound simple, but it is one of the great shifts in modern astronomy. The old sky was often studied object by object, choose a star, point a telescope, gather light. The new sky is increasingly surveyed in motion, scan wide fields, compare images, detect the unexpected. Let the universe interrupt you. This approach has opened a flood of transient discoveries, from supernovae and colonovae to tidal disruptions and mysterious fast events that do not yet have comfortable homes. And perhaps that is why the cow became such a fitting doorway into FBOTs. It was not just one strange explosion. It represented a new way of meeting the universe. A telescope built to guard against nearby asteroids found a violent event in a distant galaxy. A random name became a memorable nickname. A brief blue flash became a global observing campaign. A transient that could have been missed in an earlier age became one of the most studied mysteries of its kind. The cow showed that the sky is not merely full of objects. It is full of events, and some of those events happen on timescales that demand attention right now, even if right now is a very strange phrase for light that travelled 200 million years to get here. So when astronomers met the cow, they were not simply meeting a single explosion. They were meeting a problem that would lead them toward an entire class of objects. The cow made clear that some cosmic blasts are too fast for ordinary supernova habits, too blue for a cool fading shell, too bright for simple expectations, and too energetic in X-rays and radio waves to be dismissed as a small variation on a familiar theme. It stood there in the data, bright and brief, asking scientists to explain how a star or compact object could produce so much light so quickly and then change before the explanation had settled. Start with the name itself, because for once, astronomy has given us a label that works almost like a little instruction manual. Fast Blue Optical Transient. 4 words, each one plain enough on its own, and yet together they describe something that has made astronomers scratch their heads, check their data, and occasionally wonder whether the universe is deliberately trying to keep them humble. Fast means it changes quickly. Blue means it is hot. Optical means it was first noticed in visible light. The light our eyes would see if our eyes were giant telescopes with excellent scheduling software. Transient means it does not last. It appears, brightens, fades, and then becomes something else, or perhaps becomes too faint for us to follow. A fast blue, optical transient is not just an object. It is an event. It is a brief performance by matter under extreme conditions, and the frustrating part is that the curtain drops before we can see all the machinery backstage. That is the first thing that makes these events unusual. They are defined by behaviour before they are defined by cause. When astronomers say white dwarf, they are talking about a kind of stellar remnant. When they say neutron star, they they are talking about an object with a specific physical nature, even if that nature is so dense and strange that it makes everyday matter seem like whipped cream. But when they say fast blue optical transient, they are often saying here is what it looked like from Earth. It got bright quickly, it was very blue, it showed up in optical surveys, it faded away. That is a description, not a full explanation. It is like hearing a crash in the kitchen and writing down, sudden loud plate-related incident, before you know whether a cat, a shelf, or your own elbow is responsible. To understand why that matters, it helps to compare FBOTs with the more familiar explosions we call supernovae. A supernova is already one of the most extreme events in the universe. It can mark the death of a massive star, the collapse of a core, the release of an enormous amount of energy, and the scattering of heavy elements into space. Supernovae can create neutron stars and black holes. They can seed galaxies with oxygen, silicon, iron, and many of the atoms that later become planets, oceans, and people wondering why their kettle takes so long to boil. So, when astronomers call something stranger than a supernova, they are not saying it lightly. A supernova is already a cosmic heavyweight. An FBOT is unusual because it seems to take some features of a supernova and then twist them out of their normal timing, colour, brightness, and energy pattern. Most supernovae brighten over days to weeks and fade over weeks to months. They're like curves, which are graphs showing brightness over time, often have recognisable shapes. Different types of supernovae have different patterns, but the general idea is familiar enough that astronomers can often classify them by how they rise, how they fall, and what features appear in their spectra. FBOTs do not politely follow those expectations. The brightest ones can reach their peak in only a few days, sometimes less than a week. Then they decline rapidly, at least in optical light. That speed is not just an aesthetic detail. It tells scientists that the region producing the light may be relatively compact, or that the energy is escaping unusually quickly, or that the standard picture of a large expanding cloud powered mainly by radioactive decay is not enough. A fast light curve is like a stopwatch placed on the explosion. It says the engine must be small, efficient, exposed, or very strange. Think of a normal supernova as a great thick lantern wrapped in layers of fabric. The energy is produced inside, but the light has to work its way out through expanding material. That takes time. The glow rises as the heat diffuses outward, then fades as the material expands, cools, and becomes transparent. In many cases, radioactive nickel made in the explosion decays into cobalt and then iron, helping power the light over a timescale of weeks and months. The result is not slow by human standards, of course. A star exploding over weeks is still a rather dramatic diary entry, but compared with FBOTs, it is leisurely. An FBOT is more like a bright bulb with the shade torn off. The light comes out too quickly. It does not seem content to wait for the normal diffusion schedule. Somewhere in the physics, the usual delays have been shortened. The blue colour is the next clue, and it is a very important one. In astronomy, blue usually means hot. That can feel backwards if your everyday brain has been trained by bathroom taps and weather maps, where blue is cold and red is warm. But stars and glowing gases follow different rules. A cooler star looks redder, a hotter star looks whiter or bluer. When an FBOT shines blue, especially in its early days, it is telling us that the visible material is extremely hot. In some events, temperatures can be tens of thousands of degrees. That is not simply a decorative colour choice by the cosmos. It is a sign that the explosion is energetic and that the emitting material has not yet cooled into the redder colours seen in many aging transients. What makes this even more unusual is that FBOTs can remain blue while evolving quickly. Many explosions start hot and then cool. Their colours shift as the expanding debris loses energy. But the most extreme cow-like events have shown persistent blue emission and high temperatures that are difficult to explain with a simple expanding shell. If a firework fades, you expect the sparks to cool. If it fades but remains oddly hot, you begin to suspect that something inside is still feeding it. That is one reason scientists keep returning to the possibility of a central engine. The blue light may not just be leftover heat from a one-time blast. It may be connected to ongoing power from something compact and energetic buried inside the debris. Then comes the brightness. Some FBOTs are not just fast and blue, they are very luminous. A T2018 cow, the cow, became at least about 10 times brighter than a typical supernova in only a few days. That is an astonishing combination. Fast events are often expected to involve less material or smaller emitting regions, which can limit how much total light they produce. Extremely luminous events often require large energy reservoirs, and many of those unfold over longer timescales. FBOTs seem to ask for both, rapid release and enormous brightness. It is a bit like seeing someone sprint past you while carrying a grand piano. The speed alone would be impressive. The piano makes it suspicious. Brightness in astronomy is not just about how dazzling something looks, it is an energy problem. If an event shines brightly, that energy has to come from somewhere. In ordinary supernovae, radioactive decay can supply much of the visible light. In some superluminous supernovae, extra energy may come from interaction with surrounding material or from a central engine such as a magnetaire. In FBOTs, the combination of quick rise, high luminosity, blue temperature, and rapid changes makes it hard to rely on one simple power source. You can try to make enough radioactive nickel, but then you may run into problems with the timescale and the amount of ejecta. You can invoke interaction with dense gas around the star, but then you must explain how that gas got there, why it is arranged the way it is, and why the event still shows other strange signals. You can add a compact engine, but then you have to explain how we see it so soon and what kind of object is doing the powering. Every solution brings luggage. The spectra add another layer of difficulty. A spectrum is what you get when you spread light out by wavelength, like making a cosmic barcode. It can tell you what elements are present, how hot the material is, how fast it is moving, and sometimes what kind of explosion you're looking at. Many supernovae have recognizable spectral lines. Hydrogen lines, helium lines, silicon lines, and other features help classify them. Early FBOT spectra can be relatively featureless, dominated by a hot blue continuum rather than a neat set of chemical fingerprints. That is frustrating because astronomers love fingerprints. A featureless spectrum says, yes, this is hot, but it does not immediately say what star died, what layers were ejected, or what exact process produced the light. It is like receiving a letter with perfect handwriting and no signature. When features do appear, they can still be hard to interpret. Broad lines can suggest fast-moving material. Narrow lines may indicate interaction with slower material around the star. Changes over time may reveal the explosion becoming more transparent, but the early absence or weakness of familiar features means that FBOTs resist quick classification. They are not simply Type 1a supernovae. They are not ordinary Type 2 supernovae. They are not comfortably placed among normal stripped envelope supernovae. They overlap with several categories but do not settle neatly into any of them. This is one of the reasons the word transient matters. It keeps the label flexible while scientists argue about the cause, hopefully politely, though astrophysical debates can be very energetic for people discussing light curves. Another unusual feature is the role of other wavelengths. An optical transient can be strange in visible light, but FBOTs become much more interesting when observed in X-rays and radio waves. The cow, for example, was not just a bright optical event. It was detected across a wide range of the spectrum from radio to high-energy radiation. X-rays are especially important because they often point toward very energetic processes in compact regions. A strong variable X-ray source can suggest accretion onto a black hole, activity from a newborn neutron star, shocks, or some other central power source. Radio waves can reveal fast outflows slamming into surrounding gas, telling astronomers about the speed of the ejector and the density of the environment. When an explosion speaks in optical light, X-rays and radio all at once, it is not giving one clue, it is dropping clues all over the floor. The X-ray behaviour is particularly suspicious in the best possible scientific sense. In a simple supernova, X-rays may be produced when the expanding debris crashes into material around the star, or through other shock-related processes. But in some FBOTs, the X-ray luminosity and variability seem too intense or too persistent for the simplest versions of that picture. The cow showed evidence that many researchers interpreted as an embedded X-ray source, something shining from within the debris. Later analyses even found signals that may point toward a compact object, such as a neutron star or black hole. This does not mean the answer is settled. It means the event is forcing scientists to consider a central engine as a serious possibility. And central engines are where things become wonderfully strange. A central engine changes the story. Instead of a star exploding once and then simply cooling, we may have a star exploding while something inside continues to feed energy into the system. A newborn magnetar could spin rapidly, with a magnetic field so strong it channels energy into the surrounding debris. A newly formed black hole could accrete fallback material, turning gravitational energy into radiation and outflows. A compact object in a binary system could merge with or tear apart a companion. In each case, the visible FBOT would be the outer sign of a deeper engine. It is not just an explosion. It is an explosion with machinery still running inside. Imagine a house collapsing, and then discovering that the furnace in the basement is still roaring. You would want to understand that before writing the final report. The surrounding environment is another clue. Massive stars often shed material before they die. Some lose their outer hydrogen layers through winds or interactions with companion stars. Some may experience violent eruptions before core collapse. If an explosion occurs inside a dense shell or cloud of material the star expelled earlier, the blast can collide with that material and convert kinetic energy into light. This is called circumstellar interaction. It can make an event brighter and can shape its spectra, radio emission and X-rays. FBOTs may involve unusual circumstellar environments, perhaps created shortly before death. That raises another question. What kind of star throws off just the right material, at just the right time, in just the right arrangement, and then explodes into it? Stars apparently can be very dramatic planners. Speed also affects how much material can be involved. A fast rise often implies that the optical light is escaping from a relatively small amount of rejector or from a compact emitting region. If there were a huge mass of thick material, the light would take longer to diffuse out. So some models suggest FBOTs may eject less mass than ordinary massive star supernovae, or that the geometry is unusual, allowing radiation to escape along certain directions. Geometry is easy to underestimate. We often imagine explosions as round because round is simple and comforting. A star is round, so surely its explosion is a sphere expanding nicely in every direction, like a cosmic balloon. But real astrophysical explosions can be messy. Rotation, magnetic fields, disks, jets, companions, and uneven surrounding material can all break the symmetry. An explosion may be flattened, lopsided, channeled, or clumpy. If we view it from one direction, it may look very different than it would from another. That possibility matters because FBOTs may not only be physically unusual, they may also be observationally selective. We might notice the most extreme ones when the geometry gives us a clear view into the hot inner region. If a jet or funnel points partly toward us, the event may look brighter and bluer. If dense material blocks our line of sight, the same underlying event might appear different or be missed. This complicates everything naturally. Astronomers do not get to walk around a distant explosion and inspect it from the side. They have one viewpoint, one set of photons, one line of sight through space. It is like trying to understand a theatre production, by peeking through a keyhole while the stage is on fire. Rarity is another reason FBOTs are so unusual. Cow-like luminous FBOTs appear to be far less common than ordinary core collapse supernovae. That rarity tells us that whatever creates them requires special conditions. Not every massive star dies this way. Not every compact object interaction produces this signature. Not every galaxy offers these events often enough for easy study. Rare objects are scientifically valuable because they point to uncommon pathways in nature, but they are also difficult because small samples make it hard to know which details are essential and which are just quirks of one event. With only a limited number of well-observed examples, each FBOT becomes important, but also dangerous to overinterpret. One cow is a mystery. Several cow-like events begin to suggest a class, but the class itself may contain multiple kinds of explosions wearing similar blue coats. This is a major challenge. The name FBOT may include events that do not all come from the same physical process. Some may be unusual, core collapse supernovae with central engines. Some may be tidal disruption events involving smaller black holes. Some may involve compact objects merging with massive stars. Some may involve dense shells, disks, or binary interactions. They share visible properties, but shared appearance does not always mean shared origin. In everyday life, a kettle, a radiator, and a laptop charger can all feel hot, but you would not explain them with the same diagram unless you enjoy confusing electricians. In astronomy too, similar light curves can sometimes hide different engines. That makes classification tricky. Astronomers often rely on patterns. If an object rises this way, shows these lines, fades that way, and appears in this environment, it probably belongs to this class. FBOTs interfere with that method. Their optical behaviour may suggest one thing, while their X-rays suggest another. Their spectra may refuse to give enough chemical detail. Their host environments may hint at massive stars but not prove it. Their radio emission may point toward fast ejector and dense material. Their late-time behaviour may reveal something still active. Each clue matters, but the clues do not always line up into a single clean picture. It is less like solving a jigsaw puzzle and more like discovering that several puzzles have been mixed into the same box, and one of the pieces appears to be from a toaster. The short timescale also changes how scientists must study them. If an FBOT is discovered late, the earliest clues are gone. The rise time, early colour, initial spectra, and first X-ray behaviour may be the most important pieces, but they happen quickly. This is why wide-field surveys and rapid follow-up are essential. Astronomers need to catch the event as soon as possible, alert other telescopes, and gather data before the object changes. It is not enough to build powerful telescopes. You need a fast communication network, flexible observing plans, automated detection systems, and people ready to respond. Modern transient astronomy is as much about timing as sensitivity. The telescope must be large enough to see, but the system must be quick enough to notice. FBOTs also force scientists to think about what happens just before a star dies. This is one of the most interesting hidden questions. If an FBOT involves a massive star, then the star's final years, months, or days may be crucial. Did it lose mass shortly before collapse? Did a companion strip away its outer layers? Did the core change in a way that triggered eruptions? Did waves or instabilities inside the star push material outward? The final stages of massive stars are hard to observe directly because they are rare, short, and often hidden inside dusty or distant environments. But FBOTs may be bright signposts of those final unstable moments. They may tell us that some stars do not approach death calmly. They stagger, shed, interact, and restructure their surroundings before the end. There is a gentle irony here. FBOTs are brief, but they may reveal long histories. A flash that lasts days can carry information about a star that lived for millions of years. The dense material around it may have been shaped by winds over time, or by a companion star orbiting nearby. The compact engine may depend on the core's rotation, magnetic field, mass, and previous evolution. The location in the host galaxy may reflect where the star was born and how it moved. The transient is short, but the cause is not. It is like hearing one sudden note from another room, and realizing it belongs to a whole song that has been playing quietly for ages. This is why FBOTs are so difficult and so useful. They are not strange in only one way. If they were merely fast, astronomers could focus on timescale. If they were merely blue, they could focus on temperature. If they were merely bright, they could focus on energy. But they are fast, blue, luminous, rare, spectrally odd, and often active in X-rays or radio. Each unusual trait narrows the possible explanations, but the combination also makes simple explanations fail. The universe seems to have built an event that sits at the intersection of stellar death, compact objects, circumstellar material, and high-energy astrophysics. It is not one locked door, it is a hallway of locked doors, and every key opens only half of one. For a sleepy mind, perhaps the easiest way to hold it is this. A normal supernova is a star's grand ending, bright and powerful, but often understandable within a familiar framework. An FBOT is a grand ending with a hidden complication. Something happens too quickly. Something stays too hot. Something shines too strongly. Something at the center may keep working. Something around the star may be arranged in an unusual way. And because the whole display fades so fast, astronomers have to gather the evidence while it is still changing under their instruments. That is what makes fast blue optical transients so unusual. They are not simply explosions. They are fast-moving clues to some of the most extreme transitions in the universe, the moments when massive stars collapse, compact objects are born, hidden engines switch on, or matter is torn apart under gravity's most severe rules. They remind us that stellar death is not one neat process. It is a family of endings, some common, some rare, some slow enough to watch carefully, and some so quick that they feel like a flash of blue lightning across the dark. What makes these explosions brighter, bluer, and faster than supernovae is not one simple trick. As much as astronomers might appreciate the universe handing over a neat answer with a label and perhaps a small diagram, it is more like several difficult clues arriving at once. The light comes out too quickly, the temperature stays too high, the brightness climbs too far. The X-rays and radio waves suggest that something energetic may still be working after the first visible flash. And the whole event changes so fast that by the time scientists have written down one explanation, the object has already moved on to the next stage, rather like a guest at a party who keeps changing outfits while everyone is still trying to remember their name. A normal supernova is already an extreme object, so it is worth being careful when we compare anything to it. A massive star dying in a core collapse supernova releases a huge amount of energy. For a while, it can shine as brightly as an entire galaxy. Its outer layers are blasted outward at thousands, or even tens of thousands of kilometers per second. It creates and spreads heavy elements. It leaves behind a compact remnant, perhaps a neutron star or a black hole. Nothing about that is ordinary in any human sense. If one happened close to Earth, which thankfully is not part of tonight's relaxing itinerary, it would be one of the most spectacular and concerning events in the sky. But in astronomy, ordinary often means we have seen enough examples to know the general pattern, not small or boring. Supernovae are familiar giants. FBOTs are the giants that do not follow the familiar schedule. The first difference is speed. When a supernova begins, the explosion happens deep inside the star, or in the case of a thermonuclear supernova, throughout a dense stellar remnant. But the light we see does not always escape immediately. Energy has to move outward through expanding debris, and that takes time. The material thrown from the star is thick at first. Photons scatter again and again, bouncing through the debris like sleepy travellers trying to find the exit in a very crowded station. Only gradually does the light make its way out. This delay helps shape the rise of the supernova's light curve. Depending on the type, a supernova may take many days or even weeks to reach peak brightness. FBOTs do not wait that long. The brightest cow-like events can rise to maximum light in only a few days. That fast climb tells astronomers that the region producing the visible light cannot be hidden behind too much thick material, at least not in the usual way. If the ejecta were massive and opaque, the light would take longer to diffuse out. So either there is not much material in the way, or the material is arranged in an unusual shape, or energy is being released very close to the surface, or a powerful engine is forcing radiation outward through a channel. None of these possibilities is simple. Each one asks for special conditions, and special conditions are exactly where the mystery begins to grow. You can think of the difference by imagining two lamps under blankets. A supernova is like a powerful lamp wrapped in many thick layers. It takes time for the glow to push through, and the light that emerges is spread out over a longer period. An FBOT is more like a lamp wrapped in a thin torn cloth, or perhaps a lamp with a hole cut through the cover so a beam can escape. The energy is not necessarily smaller. In fact, it may be enormous, but it gets out quickly. That quick escape makes the event look sharp, sudden, and very hot. It also means the physical structure around the explosion must be different from the thick, slow, expanding shells we often rely on when explaining ordinary supernova light. This is one reason radioactive decay alone becomes hard to use as the main power source. In many supernova, a large part of the visible glow comes from the decay of radioactive nickel-56 into cobalt-56 and then into iron-56. This process releases energy that heats the expanding debris and keeps the supernova shining. It is a beautiful piece of cosmic alchemy, and it is one reason supernova light curves can be so useful. The problem is that radioactive decay has a certain rhythm. It does not usually produce an extremely fast, extremely bright, extremely blue peak all at once, unless the conditions are pushed into awkward territory. To make enough brightness, you may need a lot of nickel, but if you have lots of material, the light should usually take longer to escape. If you reduce the material to make the event faster, you may not have enough radioactive fuel to make it so bright. It is a bit like trying to make a cake that is huge, fully baked, and ready in 3 minutes. Possible in a microwave advertisement perhaps, but nature has stricter rules, so astronomers look for extra power. One possibility is shock cooling. If a star has an extended envelope or surrounding material, the initial explosion can heat it, and as that material expands, it releases a bright flash. Shock cooling can make early light that is hot and blue, and it can fade quickly. This explanation works well for some fast early signals from supernovae. But for the most luminous FBOTs, shock cooling alone may not be enough. The energy is too large, the temperature is too persistent, and the X-ray or radio behavior too active. Shock cooling may help with part of the light, but it does not easily explain the full display. It is one tool in the box, not the whole workshop. Another possibility is interaction with circumstellar material. That phrase sounds technical, but the idea is straightforward. Before some massive stars die, they lose material into the space around them. They may shed gas through powerful winds, eruptions, binary interactions, or unstable late-life behavior. When the star finally explodes, the outward-moving debris crashes into that surrounding gas. A crash at those speeds is not gentle. It converts kinetic energy into radiation, making the event brighter. It can also produce radio waves and X-rays as shocks form and particles are accelerated. If the surrounding material is dense and close enough, the light can come out quickly and strongly. This can help explain why an FBOT might be so bright. Instead of relying only on heat from the original explosion or radioactive decay inside the ejecta, the event is getting an extra boost from collision. The star has, in a sense, prepared its own crash pad before dying. Not a soft crash pad, of course. More like a wall made of gas placed at exactly the right distance to make the explosion shine. The faster debris slams into this material, an energy that would have remained as motion becomes light. That is useful for the brightness problem. It may also explain some of the radio emission. because radio waves are often produced when fast-moving material interacts with the environment around it. But circumstellar interaction also raises new questions. Where did that material come from? Why was it so close to the star? Why was it dense enough to matter? Did the star erupt shortly before it died? Was it stripped by a companion? Did it go through a common envelope phase, where two stars interact so closely that one becomes partly engulfed by the outer layers of the other? Massive stars can be unstable near the end of their lives, but arranging the right amount of material in the right place at the right time is not trivial. A model can say, there was gas around the star, but then another scientist will gently ask, lovely, how did it get there? Science is full of these polite little traps. The blue colour brings us to temperature. FBOTs are blue because the material producing the optical light is very hot. A hot black body-like source emits more strongly at shorter wavelengths, toward the blue and ultraviolet. Ordinary supernova can also start hot and blue, especially early on, but they usually cool as the debris expands. Expansion spreads the energy over a larger volume. The gas becomes less dense. The radiation field changes. The colour often shifts redward with time. FBOTs, especially the cow-like luminous ones, can remain unusually blue and hot through their early evolution. That suggests either the emitting region is being continually heated, or the light is emerging from a compact, energetic environment rather than simply cooling debris. Heat is not magic. It needs a supply. If the explosion happened once and then everything merely expanded, you would expect a fairly predictable cooling. If the event stays very hot, something may be adding energy. That something might be a shock, as ejecta collides with surrounding material. It might be a central engine, such as a newborn magnetar or a accreting black hole. It might be radiation being reprocessed from X-rays into optical and ultraviolet light. Reprocessing is a useful idea here. High-energy photons from deep inside the event may strike surrounding material, get absorbed, and then be re-emitted at lower energies, including optical blue light. The visible glow may be a translated message from a more extreme engine inside. The explosion speaks in X-rays, and the surrounding debris repeats it in blue. This idea helps connect the optical brightness to the high-energy behaviour. In the cow, for example, astronomers observed strong X-ray emission along with the optical flash. That is important because X-rays are not easy to ignore. They are produced by hot, energetic processes, often near compact objects or strong shocks. If an FBOT has a variable, bright X-ray source, it suggests that some small region is producing a lot of energy. A normal supernova can produce X-rays through interaction, but the details matter. Strong, rapidly changing X-rays make scientists wonder whether they are seeing material falling onto a compact object, or energy being released by a newly born neutron star. It is the difference between hearing a distant rumble and hearing a motor running under the floorboards. A central engine can also help with speed. If a black hole forms at the centre of a collapsing star, some of the material that fails to escape may fall back toward it. As this fallback material spirals inward, it can heat up, form an accretion disk, and release energy. Accretion is one of the universe's most efficient ways of turning gravity into radiation. Matter falls in, it speeds up, it rubs, shocks, heats, and glows. If magnetic fields and rotation are involved, some of that energy may be directed outward in jets or winds. A newborn black hole does not simply sit there like a dark marble. If it has material to feed on, it can become a compact power plant hidden inside the wreckage of the star. A newborn magnetar offers another route. A magnetar is a neutron star with an extraordinarily strong magnetic field. If it is born spinning very rapidly, it contains a huge reservoir of rotational energy. As it slows down, it can transfer energy to the surrounding ejecta. This can brighten an explosion beyond what radioactive decay would allow. Magnetars are often invoked to explain superluminous supernovae, and they are considered in FBOT models as well. But again, the timing is difficult. The The energy must come out quickly enough to match the rapid rise, yet not be trapped so long that the light curve becomes too broad. The ejector must be arranged so that the energy can escape. The engine must be powerful, but not so hidden that we only see it long after the blue flash has faded. This is why FBOTs are sometimes described as engine-driven explosions. That does not mean every FBOT definitely has the same kind of engine. It means the data often point toward ongoing central power, not merely the passive cooling of debris. Engine-driven explosions are important because they may connect several dramatic phenomena: supernovae, gamma-ray bursts, tidal disruption events, magnetar births, black hole formation, and strange stellar mergers. An ordinary supernova may be powered mainly by the blast and radioactive decay. An engine-driven event has a deeper machine at work. It is like comparing a thrown stone with a rocket. Both move outward, but one carries its own power source. Geometry may be just as important as power. In a simple picture, an explosion expands evenly in all directions. But the universe is not required to respect simple pictures. If a star was rotating rapidly, if it had a companion, if a disk formed around a compact object, or if magnetic fields shape the flow, the explosion could be very uneven. Some material might move slowly near the equator, while faster outflows escape near the poles. A jet could punch through the surrounding debris. A funnel could allow high-energy radiation to escape along one direction. If Earth happens to lie near that direction, we might see a brighter, bluer, faster event than an observer viewing from the side. The same explosion might look different depending on where you're sitting in the cosmic theatre, which is rather unfair since we cannot change seats. Asphericity can solve some problems and create others. It can explain how light escapes quickly without requiring the entire debris cloud to be thin. It can explain why different wavelengths seem to come from different regions. It can allow a compact engine to be partly visible, while much of the ejector remains thick. But it also makes modelling harder. A one-dimensional spherical model is much easier to calculate and discuss. A lopsided explosion with jets, disks, clumps, and viewing angle effects is more realistic in some cases, but much messier. Nature seems to prefer messy. Astronomers prefer solvable. This is an old disagreement. The faster part also includes how quickly FBOTs fade. After reaching peak brightness, their optical light declines rapidly compared with many supernovae. That fast fading suggests the hot optical emitting material is not massive enough to store heat for long, or that the energy input changes rapidly, or that the geometry allows the early glow to escape before the system settles into a different phase. In some FBOTs, the optical light drops while X-rays or radio emission continue, which suggests that different physical processes are taking over at different times. The blue flash may be only the first act. Beneath it, shocks may still be expanding, compact objects may still be feeding, and late-time flares may still appear long after the visible light has weakened. Radio observations are useful because they tell us about the fastest material and the environment. When ejector plows into circumstellar gas, it drives shocks. Electrons can be accelerated to high speeds, magnetic fields can be amplified, and synchrotron radiation can emerge as radio emission. Strong radio waves from an FBOT can imply fast outflows, sometimes moving at a significant fraction of the speed of light. That is another reason these events stand apart from ordinary supernovae. Very fast outflows hint at an engine or unusual explosion geometry. They suggest that not all the material is moving at one comfortable supernova speed. Some of it may be launched or accelerated in a more directed, energetic way. So, why brighter? Because FBOTs may be getting extra energy from compact engines, shock interaction, rapid accretion, or unusual collisions between ejector and nearby gas. Why bluer? Because their emitting regions are extremely hot, possibly kept hot by ongoing power or by radiation escaping from deep energetic zones and being reprocessed into optical and ultraviolet light. Why faster? Because the light may escape through lower mass ejector, compact regions, thin surrounding material, or are spherical openings, rather than diffusing slowly through a large, thick envelope? Each answer is partial. Together they form the shape of the mystery. It is tempting to imagine that there must be one master explanation, one sentence that begins, "FBOTs are simply," and then clears everything up. But the more astronomers observe, the less comfortable that becomes. Some FBOTs may truly be unusual supernovae. Some may involve black holes tearing apart stars. Some may come from compact object mergers with massive stars. Some may be powered by magnetaires. Some may represent multiple pathways that produce similar visible behavior. The family resemblance is real, but the family may have several branches. This is common in astronomy. Objects first grouped by appearance later turn out to have different origins, and objects with similar origins may look different if viewed from another angle or at another age. The comparison with supernovae is therefore both helpful and limiting. FBOTs are brighter, bluer, and faster than many ordinary supernovae because they are not simply ordinary supernovae with the brightness turned up. They appear to involve different structures, different power sources, different environments, or different viewing conditions. They push against the standard model of a large massive ejector slowly glowing from radioactive heat. They suggest that in some stellar deaths, the central compact object may be exposed early, or that the star's final surroundings may turn the explosion into a brilliant flash, or that gravity may tear apart a star in a way that imitates and exceeds a supernova's light. There is something almost personal about the speed of these events. Human beings are slow observers compared with the universe, but we are also impatient. We build telescopes that watch the sky every night because we know some secrets do not wait. FBOTs reward that vigilance. They are not like galaxies whose changes unfold over millions of years, or stars whose lifetimes stretch far beyond human history. They are cosmic emergencies visible on human timescales. A new source appears. It brightens in days. It changes colour. It throws off X-rays. It sends radio waves from shocks expanding into space. And somewhere inside the data, a compact engine may be revealing itself before the debris can hide it. A useful way to hold all of this is to imagine a normal supernova as a large, slow-opening lantern. Its light is powerful, but wrapped in mass and time. An FBOT is a lantern cracked open early, with the inner flame briefly visible. It may not be a perfect image, because the actual physics involves radiation transport, high-energy shocks, accretion, magnetic fields, and possibly relativistic outflows, which is a lot to ask from any lantern. But the image captures the key difference. FBOTs let energy out before we expect it, in colours hotter than expected, at luminosities difficult to power, and with extra signals that hint at a hidden centre. Once we accept that speed, colour and brightness may require more than an ordinary expanding shell, the next question becomes unavoidable. What is working inside the explosion? Inside this mystery, behind the blue light and the quick fading glow, astronomers keep returning to one uncomfortable idea. Maybe these explosions are not simply explosions. Maybe something is still working inside them after the first blast has already thrown material outward. Maybe there is an engine hidden beneath the debris, compact, powerful, and difficult to see directly, like a furnace burning in the basement of a house that has already collapsed around it. That word, engine, sounds almost too mechanical for the deep universe, as if somewhere inside the shattered remains of a star there is a little cosmic motor, with gears, pistons, and perhaps a tiny warning label that says, "Do not open while accreting." But in astrophysics, an engine simply means a continuing source of power. It is the thing that keeps feeding energy into the event when the initial explosion alone does not seem to explain what we observe. For Fast Blue Optical Transients, this idea matters because the visible light seems to be asking for more energy than a simple, one-time blast can comfortably provide. The blue colour sees the material is very hot. The fast rise says the light escapes quickly. The high brightness says a large amount of energy is being released. The X-rays and radio waves say violent processes are still happening in small regions or in shocks moving through surrounding gas. Put all of that together, and the picture begins to feel less like a single firework and more like a firework with a power station hidden in the smoke. The first flash catches your attention. The engine explains why the glow refuses to behave. A normal supernova does not necessarily need such an engine to shine. Many supernovae are powered, at least in their visible light, by heat deposited during the explosion and by radioactive decay. When a massive star collapses, or when a white dwarf is destroyed, new radioactive elements can form. Nickel-56 decays into cobalt-56, which decays into iron-56, releasing energy that warms the expanding debris and keeps the supernova visible for weeks or months. This is one of the reasons supernova light curves can be so useful. The fading glow is not random. It carries the rhythm of nuclear decay, expansion, cooling, and changing opacity. It is not simple exactly, because stars rarely do anything just to make exam questions easier, but it is familiar enough that astronomers can work with it. FBOTs do not seem satisfied with that familiar rhythm. Their rise is too fast. Their early light is too blue. Their brightness can be too high. Their spectra can be too odd. And in the most famous cases, their X-rays seem too energetic and too variable to ignore. If radioactive decay were the whole story, then the light should follow a more predictable pace, shaped by how much radioactive material was made and how much ejecta surrounds it. But if you try to make an FBOT bright enough using radioactive nickel alone, you often need a large amount of material. And if you have a large amount of material, the light should usually take longer to escape. The model begins to pull in two directions. Make it bright, and it becomes too slow. Make it fast, and it becomes too faint. Nature may enjoy contradictions, but models do not. This is where the hidden engine becomes tempting. A compact object can store or release energy in ways ordinary expanding debris cannot. A newly formed black hole can feed on material falling back after the explosion. A newborn neutron star can spin rapidly and pour energy into its surroundings. A magnetar can use its extreme magnetic field and rotation to energize the debris. A shock buried inside dense material can convert motion into light. These possibilities are different, but they share one important feature. They keep working after the initial blast. They turn the event from a single explosion into an explosion plus an active center. Imagine a massive star in its final moments. For millions of years, it has been held up by the pressure from nuclear fusion, turning lighter elements into heavier ones, building layer after layer inside itself. Hydrogen burns into helium, helium into carbon and oxygen. Later stages create heavier elements, and the star becomes a kind of cosmic onion, though one that would make a very bad ingredient and an even worse surprise in a lunchbox. Eventually, the core can no longer support itself. Gravity wins. The inner region collapses with terrifying speed. The outer layers respond. A shock may form. The star begins to explode. In a simple version of the story, the outer material is blasted outward, and the collapsed center becomes a neutron star or black hole. But the real story can be messier. Not all of the material escapes. Some of it may fall back toward the center. If a black hole is formed, this fallback material can spiral inward, heat up, and release energy. Matter falling toward a black hole does not quietly disappear like crumbs under a sofa. It forms an accretion flow, it speeds up, it rubs against itself, it heats to extraordinary temperatures, it can produce X-rays, launch winds, and perhaps drive jets. A black hole is dark only when it has nothing nearby to feed on. Give it matter, and the region around it can become one of the brightest engines in the universe. That is one possible engine for an FBOT, a newborn black hole feeding immediately after the death of a star. This idea is powerful because it can explain why the event might remain energetic after the first explosion. The black hole itself is invisible, but the falling material is not. As gas spirals inward, gravitational energy is converted into heat and radiation. Some of that energy may escape as X-rays. Some may be absorbed by surrounding debris and reprocessed into optical and ultraviolet light. Some may push material outward in winds. If the debris is not too thick, or if the geometry creates openings, we might see signs of this engine unusually early. The blue flash becomes a surface glow created by a deeper, hotter machine. But black holes are not the only candidates. A neutron star can also act as an engine, especially if it is born spinning rapidly. A neutron star is the compressed core left after some massive stars collapse. It can contain more mass than the sun squeezed into a sphere only about the size of a city. A teaspoon of neutron star material, if you could somehow scoop it without causing several new problems, would weigh billions of tons. Its gravity is intense. Its magnetic field can be extreme. Its rotation can be astonishingly fast. Some neutron stars spin many times per second, sending beams of radiation into space like cosmic lighthouses. Others have magnetic fields so powerful that we call them magnetars. A newborn magnetar is one of the favourite suspects in many engine-driven explosion models. If it is born spinning very quickly, it holds a huge amount of rotational energy. As it slows down, that energy can be transferred to the surrounding ejector. The magnetar's magnetic field acts like a coupling between the spinning compact star and the debris around it. Energy flows outward. The ejector heats. The light grows brighter. This can help explain superluminous explosions, and it may help explain some FBOTs as well. In this picture, the FBOT is not just the star's outer layers glowing after being thrown into space. It is a glowing shell being pumped from within by a newborn magnetic heart. There is something almost eerie about that image. A star dies, but in its centre something new is born, and that newborn object is immediately powerful enough to shape the death around it. The outer explosion is expanding outward. The inner remnant is spinning down, feeding energy into the debris. The result is not a quiet corpse, but an active remnant, a compact object announcing its arrival through a flash of blue light. If ordinary supernovae are often about endings, engine-driven FBOTs may be about endings and beginnings happening at the same time. The star is gone, but the compact object has just opened its eyes, so to speak. Although if neutron stars had eyes, they would probably be made of physics we should not stare at too closely before bed. The trouble is that each engine model must explain many details at once. A black hole accretion model must explain the timing, the brightness, the X-rays, the optical colour, and why the surrounding debris allows the radiation to escape. A magnetar model must explain how much energy is injected, how quickly, and how that energy changes across different wavelengths. A shock interaction model must explain the dense material around the star, and why the shock produces the observed light. None of these options can simply wave politely and say, "I am dramatic enough." Astronomy is not impressed by drama alone, the model must fit the data. A T2018 cow made the engine idea especially attractive because of its X-rays. X-rays come from high-energy processes. In the cow, the X-ray emission was luminous and variable, which suggested that something compact and energetic was involved. A simple expanding shell can produce X-rays under some conditions, especially if it slams into surrounding material. But strong variability hints at a small source. Why? Because a large region cannot change its brightness extremely quickly all at once. Light itself has a travel time. If a source varies on a short time scale, then the region producing that variation must be small enough for different parts of it to coordinate within that time. Rapid variability is like a ruler. It measures size by timing. This is one of the clever ways astronomers study things they cannot resolve directly. They cannot zoom in on the cow's central region and take a picture of the engine. It is in another galaxy, far too distant and far too small. But if the X-rays flicker, and if that flickering happens on short timescales, scientists can infer that the source is compact. A region the size of a star system cannot flicker coherently in milliseconds. A region near a neutron star or black hole can. The light curve becomes a shadow of the hidden object scale. Time, once again, becomes a measuring tool. A particularly intriguing clue came from reports of a quasi-periodic oscillation in the cow's X-rays. A quasi-periodic oscillation is a repeated signal that is not perfectly regular like a clock, but regular enough to suggest a physical process with a characteristic timescale. Around black holes and neutron stars, such signals can be associated with motion in accretion disks, spinning compact objects, or other processes very close to dense gravitational fields. In the cow, a reported high-frequency X-ray signal suggested that the energy source had to be extremely compact. It did not prove exactly what the engine was, but it strengthened the case that a neutron star or black hole was involved. It was as if the hidden engine briefly tapped out a rhythm through the debris, faint but persistent enough for scientists to notice. That phrase, hidden engine, is important because the engine is not usually sitting in plain view. It is embedded inside ejector, gas, dust, and expanding debris. The visible blue light may not come directly from the compact object. It may be reprocessed. High-energy photons from near the engine can strike surrounding material, heat it, and be emitted again as optical or ultraviolet light. This means the blue glow we see might be a translated version of deeper activity. The central engine speaks in X-rays. The debris replies in blue. By studying both, astronomers try to reconstruct the conversation. This reprocessing idea helps explain why FBOTs can look so bright in visible light while also showing signs of high-energy activity. If the engine's radiation were completely trapped, we might only see a broad, slow glow after the energy diffused out. If it escaped too easily, we might see mostly X-rays and little optical light. FBOTs may occupy a delicate middle ground. Enough material surrounds the engine to absorb and re-emit energy, but not so much that the light is delayed for weeks. The result is a fast, luminous blue transient. It is a timing trick performed by matter, opacity, and geometry. The universe covers the engine just enough to make it glow, but not enough to hide it completely. Geometry may decide how much of the engine we see. If the explosion is not spherical, radiation may escape more easily in some directions. A compact object might launch a jet or wind that clears a path through the debris. A star that was spinning rapidly or interacting with a companion might explode into a lopsided environment. Dense material could be concentrated around the equator, while the poles are more open. If Earth happens to line up near one of those clearer directions, we may see a hot, fast blue flash. From another angle, the same event might look dimmer, redder, slower, or perhaps not be recognized as an FBOT at all. This is a slightly unsettling thought. Some mysteries may depend not only on what happened, but on where we happen to be watching from. The engine might also be connected to material the star lost before it died. Massive stars are not always calm in their final years. Some shed powerful winds, some have eruptions, some are stripped by companions, some enter phases where their outer layers become unstable. If a star surrounds itself with dense gas before collapse, the explosion runs into that gas almost immediately. The collision can create shocks, radio emission X-rays and extra light, but if there is also a central engine, the situation becomes even richer. The engine powers radiation from inside. The blast interacts with material outside. The debris expands between them. Everything is moving, heating, thinning, and changing. A single telescope image catches only one surface of a deeply layered event. This is why FBOTs can be so difficult to interpret. The hidden engine may not be working alone. It may be one part of a larger arrangement involving the dying star's final mass loss, binary companions, compact remnants, accretion disks, jets, and shocks. A black hole could form and feed while ejector crashes into nearby gas. A magnetar could inject energy while the debris reprocesses X-rays into blue light. A compact companion could merge with a star, creating an engine-like source inside an already disturbed envelope. Each scenario can create a fast bright transient under certain conditions. The challenge is deciding which conditions match the real events. The cow was close and bright enough to make this conversation serious. Other FBOTs have added more clues. Some have shown strong radio emission, implying fast material and dense environments. Some have shown X-ray activity. Some have appeared far from the centres of their host galaxies, complicating simple tidal disruption explanations involving supermassive black holes. Some, like the event nicknamed the Tasmanian Devil, produced repeated flares long after the original explosion, as if the central object kept coughing energy into view. These later behaviours matter because an ordinary one-time explosion should fade in a relatively understandable way. If an object flares again and again, scientists begin looking for something that can restart, persist, or pulse. Engines can do that. Cooling debris usually cannot, at least not without help. Still, scientists are cautious. A hidden engine is a compelling idea, but it is not a single finished answer. Saying central engine is a little like saying there is something cooking in the kitchen. It tells you there is activity, but it does not tell you whether dinner is soup, toast, or an experimental disaster involving too much garlic. A black hole engine and a magnetar engine can both inject energy, but they do it differently. Accretion can be messy, variable, and dependent on how material falls inward. A magnetar spin-down can follow a different energy pattern. Shock interaction can mimic some engine-like behaviour. To identify the engine, astronomers need detailed observations across time and wavelength, and even then the answer may remain uncertain. There is also the possibility that FBOTs are not one thing. Some may be powered by newborn black holes, others by magnetars, others by shocks in dense material, others by tidal disruptions or compact object mergers. The visible label, Fast Blue Optical Transient, may gather together events with similar appearances but different inner causes. This happens often in science. We first classify by what we can see. Later, as better data arrive, we realise the visible family has hidden branches. In the early days of astronomy, many fuzzy objects were called nebulae. Some turned out to be gas clouds inside our galaxy. Others turned out to be entire galaxies far beyond the Milky Way. The word was useful, but it covered different realities. FBOT may be similar, a useful label for a strange glow while we learn what engines are hiding beneath it. For the listener drifting gently through this, perhaps the most important idea is that the engine is the reason FBOTs feel alive after the explosion. Not alive in the biological sense, of course. No cosmic cow is wandering through Hercules blinking in X-rays and asking for hay, but alive in the physical sense of ongoing activity. Something continues, matter falls, a compact object spins, a shock pushes outward. Radiation is absorbed and reborn. The event is not finished at the moment of detonation. It evolves because the centre still matters. This makes FBOTs valuable for understanding the births of compact objects. Usually the formation of a neutron star or black hole is hidden. A massive star collapses, the explosion expands, and the remnant is buried beneath ejecta. By the time astronomers can infer what remains, the earliest moments are gone. But in FBOTs, the ejecta may be low in mass, asymmetric, or arranged in a way that lets central radiation escape early. That means scientists may be seeing signs of a compact object almost immediately after its formation. If true, that is extraordinary. It means a brief blue transient could be a window into one of the most important transformations in the universe. Ordinary stellar matter becoming an object ruled by extreme gravity, nuclear density, and magnetic fields beyond everyday imagination. A newborn black hole would tell one story. It would suggest that the star's core collapsed beyond the neutron star stage, forming an event horizon. Material falling back would reveal itself through accretion. If jets or winds formed, they might shape the debris and drive shocks. A newborn neutron star or magnetar would tell another story. It would mean the collapsed core survived as an ultra-dense object, spinning rapidly and perhaps magnetically powering the explosion from within. Both outcomes are possible after massive star death. FBOTs may help reveal which path occurred in cases where the early light is fast enough and bright enough to expose the inner process. There is a kind of cosmic modesty in all of this. The universe does not show us the engine directly. It gives us flickers, colours, spectra, radio curves, X-ray changes, and fading optical light. It gives us clues that arrive after travelling for millions or hundreds of millions of years. It gives us events that last days, then asks us to reconstruct the collapse of a star, the formation of a compact object, and the structure of material surrounding it. It is a little like hearing a single splash in a dark lake and being asked to describe the shape of the fish, the height of the cliff, and whether someone dropped a sandwich. And yet, slowly and carefully, with enough observations, patterns begin to appear. The hidden engine inside an FBOT is therefore not just a solution to the brightness problem. It is the centre of the whole mystery. It explains why astronomers are so interested in these rare flashes. If FBOTs were simply fast supernovae with unusual colours, they would still be worth studying. But if they are engine-driven explosions, they may reveal black holes and neutron stars at the moment of birth. They may show how dying stars shed their outer layers before collapse. They may connect ordinary supernovae to gamma-ray bursts, tidal disruption events, magnetar-powered explosions, and other high-energy phenomena. They may be the missing bridge between several kinds of cosmic violence we once treated separately. By the time astronomers had spent a while staring at the cow, comparing its optical light, puzzling over its X-rays, following its radio glow, and trying to decide whether they were watching a newborn black hole, a magnetar, a strange supernova, or something else wearing a very convincing disguise, a larger question began to form. Was the cow alone? That matters more than it might sound at first. One strange object can be a curiosity. 2 strange objects become a pattern. 3 or 4 begin to look like a family, even if the family is the sort that turns up unexpectedly, refuses to explain itself, and has to be identified by animal nicknames because the official catalogue names are not exactly bedtime friendly. The cow had already given astronomers a prototype, a bright nearby example of a fast blue optical transient that rose quickly, shone hot and blue, and produced powerful signals across the electromagnetic spectrum. But a prototype can be misleading if it is the only one you have. Imagine trying to understand all birds after meeting only a penguin. You might conclude that birds are excellent swimmers, questionable flyers, and unusually formal dressers. You would not be entirely wrong, but you would be missing sparrows, eagles, owls, and that one pigeon outside the train station who appears to have made several poor life choices. In the same way, the cow might have been one odd event, one rare accident, one peculiar combination of a dying star and a hidden engine. To understand whether it represented a new kind of cosmic explosion, astronomers needed more examples. And more examples did come, though not in great numbers. That is part of the difficulty. Luminous cow-like FBOTs appear to be rare. Surveys have found many fast blue transients in a broad sense, some of which are ordinary supernovae caught early or unusual members of known classes. But the truly cow-like events, the ones that are fast, luminous, blue, spectrally strange, and often loud in radio or X-rays, are much harder to find. They are brief. They are uncommon. They require rapid follow-up. It is not enough for the sky to produce them. We must also be looking at the right place at the right time, with the right instruments, and then respond before the event has changed too much. The universe is not short of drama, but it does not always send calendar invitations. One of the most important early relatives was nicknamed the koala. Its formal name, ZTF18ABVKWLA, is the kind of name that makes koala feel not only charming, but almost medically necessary. It was discovered by the Zwicky Transient Facility, or ZTF, a survey designed to catch changing objects in the night sky. Like the cow, the koala rose quickly and appeared very blue. It had a hot, nearly featureless spectrum near peak brightness. It faded quickly. It also had a luminous radio counterpart, which made astronomers pay close attention because radio emission often tells us that fast material is running into surrounding gas. The koala was not simply a little blue flash, it was a blue flash with an energetic outward push. The koala's radio light was especially interesting. Radio waves from an explosion can reveal something that optical light alone cannot: the behaviour of the fastest ejector and the density of the material around the blast. When material from an explosion moves outward at high speed and slams into gas surrounding the star, it drives a shock. That shock can accelerate electrons and amplify magnetic fields, producing synchrotron radiation, which is a very scientific way of saying that charged particles are being forced into energetic spirals and giving off radio waves. If the radio emission is very luminous, it suggests that the outflow is powerful and that the environment is not empty. The koala seemed to have a fast-moving component, perhaps moving at a substantial fraction of the speed of light, and that pushed it closer to the cow-like category of engine-driven events. The host galaxy of the koala also mattered. It was found in a starburst dwarf galaxy, a small galaxy actively forming stars. That kind of setting can be important because massive stars live short lives and die near regions where stars are being born. If cow-like FBOTs come from massive stars, perhaps stars that collapse directly into black holes or produce newborn magnetars, then star-forming dwarf galaxies would not be surprising homes. They would be places where massive stellar deaths are more likely. This does not prove the model, of course. Astronomy rarely hands out proof that easily, but it does make the massive star explanation feel more comfortable than it would if all these events were found in old quiet galaxies full of aging stars and very little new star formation. At the same time, the koala did not make the mystery simpler. It looked similar to the cow in important ways, but not identical. That is how real cosmic families tend to work. They share features, but they do not behave like copies made on a printer. The koala supported the idea that the cow was not completely alone. It suggested that there were other fast blue luminous events with powerful radio emission and hot early spectra. But it also reminded astronomers that each event has its own environment, timing and energy budget. The family resemblance was there, but the family portrait was still blurry. Then came the camel, another event with a name that would be almost adorable if it were not tied to a violent explosion in another galaxy. The camel, formerly AT202OXND or ZTF20ACIGMEL, became particularly important because it was found and confirmed in real time as a clear analogue of the cow. That phrase, real time, matters. Many cosmic events are recognised in detail only after the fact, when astronomers search through data and reconstruct what happened. But the camel was caught early enough for astronomers to organise follow-up observations while the transient was still young. For an FBOT, that is essential. Catching it late is like arriving at a play after the main character has already explained the plot and left through a window. The camel shared several key properties with the cow. It had a fast optical rise. It maintained a high temperature. It lacked the kind of second broad peak that might be expected if a larger radioactively heated stellar envelope were powering a more standard supernova display. It showed extremely luminous radio, millimeter, and X-ray emission. And it appeared in a dwarf galaxy host. These similarities made it one of the strongest arguments that cow-like events are not merely random odd supernovae, but a distinct phenomenon or at least a distinct branch of explosive stellar behaviour. The camel did not solve the cow, but it said very clearly that the cow had company. The radio and X-ray behaviour of the camel became another key piece of evidence. Observations followed it from days to hundreds of days after the explosion, revealing luminous radio emission and bright soft X-rays that faded rapidly. The radio suggested a high-velocity outflow moving into dense circumstellar material. The X-rays seemed to represent a separate component, not just an easy extension of the radio producing shock. That separation is important because it hints that more than one physical process is at work. The radio may come from the shock where outward moving debris hits the environment. The X-rays may come from deeper inside, perhaps from accretion onto a compact object or activity from a newly formed neutron star. Once again, the idea of a hidden engine stepped forward and politely refused to leave. The camel also helped sharpen the debate about what creates these events. If you have only the cow, tidal disruption models, strange supernova models, magnetar models, and black hole fallback models all remain on the table. With the camel added, some patterns became more meaningful. A dwarf star-forming host points toward massive star origins. Fast evolution and high temperature point toward low-mass ejecta, or unusual geometry. Luminous X-rays and radio emission point towards central engines and fast outflows. The lack of a normal broad radioactive peak pushes against ordinary supernova explanations. The camel did not choose one answer, but it made some answers more attractive and others more strained. In science, that is often progress. Not a door opening all at once, but a hallway narrowing. There were other members and near members in this growing zoo as well. CSS 161010, not blessed with an animal nickname as memorable as the others, showed a fast blue optical transient with a powerful outflow moving at mildly relativistic speeds. AT2020MRF showed luminous X-ray and radio behaviour, again suggesting that cow-like events might be engine-driven. These objects widened the context. They suggested that the cow, koala and camel were not isolated sparks, but part of a rare class of fast energetic transients that share certain features while varying in detail. Each new event added another data point, another curve, another spectrum, another chance to test whether the hidden engine idea could survive contact with reality. But then the Finch arrived and made everything stranger in a different way. The Finch, formerly AT2023FHN, was another luminous fast blue optical transient. Its light behaved in ways that placed it in the broader FBOT family. It was fast, it was blue, it was luminous. It was the sort of event that should have helped astronomers refine their picture. Instead, its location raised a new problem. Earlier cow-like events had generally been found close to star-forming host galaxies, which fit the idea that they came from massive stars dying young. The Finch was found far from the centres of the nearest candidate host galaxies. Hubble observations showed it was offset by a large distance from the two closest galaxies at similar redshift. That is not where astronomers expected such an event to be, if the simplest massive star picture were always correct. This is a serious clue because location tells a story. Massive stars do not live very long. They form, burn brightly and die quickly, often before they can travel far from their birthplaces. So if an explosion comes from a very massive star, we often expect it to happen in or near a star-forming region. If a fast blue transient appears far out in intergalactic space, or in the outskirts far from obvious star formation, that expectation becomes harder to maintain. It does not make a massive star origin impossible. A runaway star could be ejected from its birthplace. A faint dwarf galaxy could be hidden below detection. A compact binary system could travel before merging. A globular cluster or old stellar population could be involved. But the simple picture becomes less simple, and simple pictures, once disturbed, rarely go quietly back to sleep. The Finch opened the possibility that not all LFBOTs come from the same progenitor channel. Perhaps some are massive star deaths in star-forming dwarfs, while others involve compact objects in older or more remote environments. Maybe some are tidal disruptions by intermediate mass black holes outside galactic centres. Maybe some involve stellar mergers, neutron stars, white dwarfs, or black holes in systems that have drifted away from their birthplaces. The Finch did not declare one of these answers correct. It simply made the family more complicated. It showed that the growing FBOT group might not be a tidy row of siblings. It might be more like a reunion where several cousins have arrived from different branches and everyone has the same eyes but very different stories. This is where the animal nicknames become oddly useful. The cow, the koala, the camel, the finch, and later the Tasmanian devil are easier to hold in the mind than strings of letters and numbers. The names are informal, but they help us remember that each event is distinct. The cow was the bright nearby prototype. The koala brought a luminous radio counterpart and a starburst dwarf host. The camel offered a real-time cow analogue with strong multi-wavelength behaviour. The finch challenged the usual environmental picture by appearing far from obvious host galaxy star formation. The Tasmanian devil, which we will come back to in a later stretch of the story, added strange repeated flares after the initial explosion. It is almost as if the universe saw that astronomers were building a category and decided to test how flexible that category could be. A growing family can be comforting because patterns become clearer, but it can also be unsettling because the pattern may reveal that the first definition was too simple. At first, FBOTs may sound like one kind of thing: Fast Blue Optical Transient. But as more examples appear, astronomers have to ask whether they are seeing one physical class or several different physical classes that happen to look similar at early times. This is a familiar challenge in astronomy. We classify first by observation, because observation is what we have. Later, as data improve, we try to classify by cause. Those are not always the same. A blue fast light curve is an appearance. A newborn black hole, magneta, tidal disruption event, or shock-interacting supernova is a cause. The appearance may be shared by several causes, especially when the event is brief and the earliest details are hard to capture. The Zwicky Transient Facility and other surveys are central to this story because they find the fleeting events that older observing strategies could miss. A wide-field survey repeatedly images large areas of sky and compares them with previous images. When a new source appears, the system can alert astronomers quickly. This is exactly the kind of machinery needed for FBOTs. Without frequent sky monitoring, an event that rises and fades in days can slip through unnoticed. By the time someone looks again, the blue flash is gone, and all that remains is a faint afterglow, or nothing at all. The family grows only because our instruments have become patient in a very specific way. They do not stare at one object forever. They keep returning to the whole sky and asking, what changed? That question is transforming astronomy. The universe used to be imagined as mostly still, at least on human timescales. But survey astronomy has revealed that the sky is restless. Stars flare, asteroids move, supernovae explode, black holes feed, neutron stars merge, tidal disruption events brighten around galactic centers. Strange flashes appear in dwarf galaxies. Other strange flashes appear far from galaxies where they are not supposed to be. The sky is not a painting. It is a weather system, though one spread across unimaginable distances and powered by gravity, nuclear physics, magnetic fields, and the occasional dying star having an extremely difficult evening. The rarity of cow-like FBOTs also means every new event carries heavy responsibility. If only a few are well observed, then each one can influence theories strongly. The cow made central engines exciting. The koala strengthened the radio outflow connection. The camel supported the idea of a distinct cow-like phenomenon. The finch complicated the host environment story. But with small samples, scientists have to be careful. One odd location might represent a new channel, or it might reflect a hidden host, a projection effect, or a rare runaway system. One strong radio detection might reveal a fast engine-driven outflow, or it might reflect a particularly dense environment around the star. The data are precious, but they are not infinite. Astronomers have to hold their conclusions gently, like a cup of very hot tea on a wobbly table. That is why the growing family is so important. The more examples we find, the more we can ask statistical questions. How often do these events happen compared with normal core collapse supernovae? What kinds of galaxies host them? Do they prefer low metallicity dwarf galaxies, like some gamma ray bursts and superluminous supernovae? Are they always associated with star formation, or do some occur in older environments? How often do they show X-rays? How often do they show luminous radio emission? Do all of them have hidden engines or only the brightest ones? Are the animal-named events the most extreme tip of a broader iceberg? And if they are the tip, what does the rest of the iceberg look like? There is also a selection effect quietly lurking behind the whole story. We notice the brightest, fastest, most dramatic events most easily. The cow was nearby enough and bright enough to attract enormous attention. The koala and camel were caught by surveys and followed up because they stood out. The finch drew attention because of its unusual location. But there may be fainter or more distant events that we miss, or events that are not recognised because they fade before anyone obtains a spectrum. The family we know may be biased toward the loudest members, the ones shouting in blue light, X-rays and radio waves. There may be quieter relatives whose engines are weaker, whose debris is thicker, or whose geometry points the wrong way. The universe may have more cows, koalas, camels and finches than our catalogues currently admit, though thankfully not in the literal sense, because intergalactic livestock would raise several practical concerns. The animal names also hide a serious truth about how science handles confusion. Naming something does not mean understanding it. It gives the mystery a handle. Once the cow had a name, scientists could compare other objects to it. Once the koala and camel joined, researchers could speak of cow-like events, luminous FBOTs, and a rare engine-driven subset. Once the finch arrived, the category had to stretch. Names let us gather data, organise thought, and build conversations. But the names do not solve the physics. They are labels on sealed boxes. The real work is opening them without losing track of what was inside. As the FBOT family grows, the hidden engine idea remains one of the strongest threads connecting the brightest events. The koala's radio emission suggests a fast outflow. The camel's luminous radio millimeter and X-ray emission suggests multiple energetic components. The cow's X-rays point toward compact central activity. The Tasmanian devil's late flares suggest an engine that can persist or restart. Even the finch, strange location and all, belongs to the discussion because its fast blue luminosity asks for a powerful source. The details differ, but the same question keeps returning. What compact machine, shock, collision, or collapse can release so much energy so quickly and leave these clues across the spectrum? That question has not become easier with more examples. It has become richer. The cow alone could have been explained with a special model made just for it, a one-off cosmic accident. The koala and camel made that less satisfying. They showed that cow-like behaviour repeats. The finch made a single progenitor story less comfortable. It showed that the environments may vary. The Tasmanian devil added late-time activity that looked almost impossible for a simple fading explosion. Together, the family is not forming a neat answer so much as a map of the problem. It shows which paths are likely, which paths are blocked, and which paths lead into deeper dark. For a listener resting here on Earth, there is something quietly wonderful about this. These events are violent beyond ordinary imagination, yet their names are gentle and almost silly. The cow, the koala, the camel, the finch. Behind each nickname is an explosion that may involve a collapsing massive star, a newborn compact object, material racing outward at enormous speeds, and radiation crossing hundreds or thousands of millions of light years. The names make them approachable, little handles for enormous events. They remind us that science is done by human beings, and human beings need ways to talk about things that otherwise come labelled as a T2018 cow or ZTF2 or a CIGMEL, which sound less like mysteries of nature and more like spare parts for a dishwasher. The growing family also reminds us that discovery rarely moves in a straight line. First comes surprise, then comparison, then classification, then complication. The cow surprises everyone. The koala and camel confirm that similar events exist. The finch complicates the environmental story. Other events add radio, X-ray, and late-time clues. The category becomes stronger and less simple at the same time. That is not a failure. That is how knowledge grows. A simple mystery becomes a structured mystery. A structured mystery becomes a set of testable models. And eventually, perhaps, enough examples will let astronomers separate the true relatives from the lookalikes. For now, the FBOT family remains small but demanding. Each member arrives quickly and fades quickly, but leaves behind questions that last for years. Each one asks astronomers to coordinate telescopes across the world and in space. Each one forces models of stellar death to account for speed, heat, luminosity, radio shocks, X-ray engines, and strange locations. The cow opened the door. The koala showed that luminous radio outflows could be part of the pattern. The camel proved that real-time discovery could catch a cow-like event as it unfolded. The finch warned that the story might not always begin in the kind of star-forming neighbourhood astronomers expected. And as more surveys come online, watching the sky with wider, faster, more sensitive eyes, the family may grow from a handful of strange animals into a proper census of rare cosmic endings. Once the first blue light has caught everyone's attention, once the telescope alerts have gone out and the graphs begin climbing in a way that makes astronomers sit up a little straighter, the real detective work moves beyond what human eyes could ever see. The optical flash is the invitation. It tells us that something hot, fast and unusual has happened. But the deeper clues come from wavelengths that never enter our eyes at all. X-rays, radio waves, millimeter light, ultraviolet radiation, all the invisible messengers that travel with the visible glow, carrying information from regions that may be hotter, smaller, faster, or more deeply buried than the blue flash itself. And with fast blue optical transients, these invisible messengers do not always behave politely. They arrive too bright, too late, too variable, too powerful, or too separate from the optical light to be explained with one simple fading fireball. This is one of the reasons FBOTs became so interesting so quickly. In visible light, they are already odd. They rise fast, shine blue, and fade quickly. But if that were the entire story, astronomers might eventually place them among unusual fast supernovae, perhaps powered by shock cooling or interaction with nearby material. The optical data alone would still be puzzling, but not necessarily revolutionary. It is the X-rays and radio waves that make the mystery harder to fold away. They suggest that the explosion is not just cooling debris. They point toward shocks, compact engines, dense surroundings, fast outflows, and interactivity continuing after the blue light begins to decline. It is as if the visible flash says, "Something exploded," and the X-rays add, "Something is still awake inside." Let us begin with X-rays, because X-rays are the part of the story that feels closest to the hidden engine. In everyday life, X-rays are the kind of light used to look through soft tissue and reveal bones, or to make dentists quietly optimistic about finding problems you did not know you had. In astronomy, X-rays usually come from very energetic places. Gas heated to millions of degrees, material falling toward black holes, shockwaves moving at enormous speeds, magnetic activity around compact objects, regions where gravity, heat, and motion are all being pushed to extremes. If a distant transient produces strong X-rays, astronomers pay attention, because X-rays often point toward the smallest and most violent regions of an event. A T2018 cow was bright in X-rays, and not just in a mild background way. Its X-ray emission was strong and variable, and that variability mattered. A source that changes quickly must be physically compact, because a large region cannot coordinate rapid changes faster than light can cross it. Imagine a giant stadium trying to turn all its lights on and off at exactly the same instant. If the stadium is enormous, signals take time to travel from one side to the other, but a small lamp can flicker quickly as a single unit. In astronomy, this idea becomes a measuring tool. If X-rays from a cosmic source flicker on short timescales, the region producing them must be small enough for that flicker to make sense. With the cow, this pushed scientists towards something compact, perhaps a black hole or neutron star, rather than a wide, smooth shell of expanding debris. That is a very important distinction. A normal supernova can produce X-rays, especially when its outward-moving material slams into gas around the star. That kind of shock interaction can heat material and accelerate particles. But the X-rays from a broad shock are not necessarily expected to flicker like a tiny central object. If the X-ray behaviour looks too bright, too irregular, or too compact, astronomers start wondering whether the emission is coming from deeper inside. Maybe material is falling onto a newborn black hole. Maybe a neutron star is injecting energy. Maybe there is an accretion disk hidden beneath the debris. The X-rays become a flashlight shining from behind the curtain, and the curtain is not quite thick enough to hide it. The cow even offered a particularly strange possible clue. A high-frequency X-ray signal, a kind of rapid, quasi-periodic rhythm. A signal like that suggests a very small source, because it repeats on a timescale of only milliseconds. Milliseconds belong to compact objects. They are the time domain of neutron stars, black holes, and gas orbiting close to intense gravity. A star the size of the Sun does not meaningfully pulse its whole body every few milliseconds. A large cloud of debris cannot neatly change on that timescale, but a neutron star can spin rapidly. Gas near a black hole can orbit quickly. Accretion flows can flicker as matter plunges inward. So when astronomers see a rapid X-ray rhythm associated with something like the cow, they do not simply shrug. They ask whether they have caught the newborn remnant tapping out its presence from inside the explosion. Of course, a rhythm is not the same as a signed confession. It does not tell us, all by itself, whether the compact object is a neutron star, a magnetar, a stellar mass black hole, or something more unusual. It does not solve the geometry or the energy budget. It does not show us a direct image of the engine. But it narrows the imagination. It says the source must be small. It says the central region may still be active. It says that whatever powered the cow was not simply a huge cloud expanding and cooling in silence. Something inside was changing quickly enough to leave a trace in X-ray light. This is where the idea of accretion becomes especially useful. Accretion means matter falling inward, usually toward a compact object and releasing energy as it does. It is one of the universe's great power sources. A black hole itself emits no light from within its event horizon, but the matter around it can shine intensely before it crosses that boundary. Gas spirals inward, heats up, forms a disk or a messy flow, and can produce X-rays as it reaches extreme temperatures. If a massive star collapses and forms a black hole, not all material may escape in the explosion. Some may fall back. That fallback material can feed the black hole, and the feeding process can power high-energy emission. In an FBOT, this could happen while the outer layers are still racing outward, meaning the event we see is a combination of explosion, fallback, accretion, and reprocessed light. A neutron star can also produce X-rays, especially if it is young, hot, magnetized, and surrounded by material. A magnetar, with its enormous magnetic field, can pump energy into its surroundings and potentially create high-energy radiation. If the neutron star is spinning rapidly, it may lose rotational energy into the debris around it. That energy can heat the ejector, drive outflows, and create signals at multiple wavelengths. The X-rays may come directly from the compact object's environment, or they may arise where winds and magnetic energy interact with the expanding material. Either way, the X-rays keep pointing inward. They tell us to look not only at what was thrown out, but at what was left behind. Radio waves tell a different part of the story. They are lower energy than optical light or X-rays, with long wavelengths that can pass through environments where visible light may be blocked. In explosive transients, radio emission often comes from shocks. When the ejector or an outflow plows into surrounding gas, it drives a shock wave, electrons are accelerated to high speeds. Magnetic fields are amplified. The electrons spiral around those magnetic fields and produce synchrotron radiation, which can appear as radio or millimeter light. If you want to understand the fastest material in the explosion and the density of the space around it, radio waves are incredibly useful. They are like footprints in the surrounding gas, showing how hard the explosion is pushing outward. For FBOTs, the radio emission has been unusually revealing. The cow produced strong radio signals. The koala was notable for its luminous radio counterpart. The camel produced luminous radio and millimeter emission over weeks to months. A T2020 MRF was also radio bright. These are not tiny decorative afterthoughts. They suggest that some FBOTs launch fast outflows into dense environments. The outflow speeds inferred from radio modelling can be a substantial fraction of the speed of light. Not quite the fully relativistic jets of classical gamma-ray bursts, but much faster than many ordinary supernova ejector components. That puts FBOTs in an interesting middle ground. They are not always gamma-ray bursts, but they may not be ordinary supernovae either. They are energetic enough to make the radio sky take notice. The surrounding environment is just as important as the outflow. Radio emission depends partly on what the explosion runs into. If a star dies in a clean, empty region, the outward blast has less material to shock. If it dies surrounded by dense gas, the shock can be bright. Strong radio emission can therefore imply that the progenitor star had lost a lot of material before it exploded, or that it lived in a dense circumstellar medium shaped by winds, eruptions, or interaction with a companion. This pushes the mystery backward in time. The FBOT is fast, but the conditions that made it may have been prepared before the explosion. The star may have spent its final years or centuries shedding material, building the stage on which its death would later become unusually bright. That idea is both helpful and troublesome. It helps because dense circumstellar material can explain strong radio emission, and can also contribute to optical brightness through shock interaction. But it is troublesome because now we have to explain the material itself. Massive stars do lose mass, but an FBOT may require a particular amount of gas at a particular distance from the star. Too far away, and the interaction happens too late. Too close, and it may change the early light in different ways. Too little gas, and the radio is faint. Too much, and the optical signal may be slower or more heavily processed. The star has to arrange its surroundings just so, like someone tidying a room before dramatically knocking the walls down. It is not impossible, but it is a clue that the progenitor's final life may have been unusual. The camel is a good example of how radio and X-rays can complicate each other. In AT202OXND, radio observation suggested a fast shock moving into a dense surrounding medium. That fits the idea of synchrotron emission from an outward blast. But the X-rays were too bright to be a simple extension of the same radio-producing component. In other words, the radio and X-rays did not appear to come from one neat physical process. The radio could be explained by the shock. The X-rays seem to need another source, possibly a central engine. That separation is a clue that the explosion has layers. The outer shock is speaking in radio. The inner engine may be speaking in X-rays. The blue optical light sits between them, perhaps shaped by energy from both directions. This is why multi-wavelength astronomy is not just a fancy add-on, it is essential. If you looked only in optical light, you might see a fast blue transient and build one kind of explanation. If you looked only in radio, you might emphasize shock interaction and dense circumstellar material. If you looked only in X-rays, you might focus on accretion or compact objects. The full picture requires all of them at once, which is inconvenient because telescopes are expensive, weather is unhelpful, schedules are crowded, and transients do not wait around while people fill out forms. But when the observations are gathered together, they can reveal whether the same model explains every part of the event, or whether the explosion is really several processes overlapping. With FBOTs, the overlap seems likely. The optical light may be created by hot material close to the explosion, perhaps heated by a central engine or shock interaction. The radio may be produced farther out, where fast ejector runs into gas around the star. The X-rays may emerge from the inner engine, or from shocks, or from some combination that changes over time. Millimeter emission may trace early dense shock regions in a way that bridges the radio and higher energy behavior. The event is not one light bulb, it is a whole system, changing as material expands, thins, collides, heats, and reveals different layers. A single name, FBOT, hides a very busy interior. A T2020 MRF made the X-ray problem even louder. This event showed extremely luminous X-ray emission, far brighter than the cow at comparable stages in some observations, and it remained detectable long after the initial optical event. It also showed variability. A fading supernova shell is not supposed to behave like a compact X-ray engine for months without a good reason. That reason may be a central engine, perhaps an accreting black hole or millisecond magnet tear. Again, the exact identity is debated, but the broad message is clear. Some cow-like FBOTs keep producing high-energy radiation in a way that ordinary supernova models struggle to explain. The phrase, ordinary supernova models, needs a little care. It does not mean supernova theory is simple or weak. Supernova themselves are complex. They involve hydrodynamics, nuclear physics, radiation transport, neutrinos, magnetic fields, rotation, and sometimes binary companions. That is not exactly a quiet afternoon puzzle. But over decades, astronomers have built frameworks for how common types of supernovae shine and fade. FBOTs push against those frameworks. Their radio can imply fast outflows and dense media. Their X-rays can imply compact engines. Their optical light can be too fast and too hot. So the problem is not that supernovae are boring. The problem is that FBOTs seem to involve extra ingredients that are not always visible in more familiar explosions. One of the most helpful ways to think about this is to separate where different signals come from. Optical light often comes from photospheric material, the region where the expanding debris becomes transparent enough for photons to escape. X-rays may come from much smaller, hotter regions, perhaps near a compact object or a strong shock. Radio waves usually come from larger radii, where the blast is expanded outward and is interacting with circumstellar material. These regions are not the same size, not the same temperature, and not necessarily powered by the same mechanism. When astronomers observe an FBOT across wavelengths, they are not looking at one surface. They are looking through a layered explosion at different depths and distances. Time adds another layer. The optical peak happens early and fades fast. X-rays may peak early, fluctuate, or persist. Radio waves can rise later, as the shock expands and becomes visible at different frequencies. Millimeter emission may appear at early times when radio frequencies are still self-absorbed. The delay between wavelengths tells us about expansion, density, absorption, and energy injection. A radio light curve is not just a brightness curve, it is a motion record. As the shock expands, it moves through gas at different distances. The changing radio spectrum can tell scientists about the size of the emitting region, the magnetic field strength, the energy in accelerated particles, and the speed of the outflow. That is a lot of information hiding inside a signal your phone also uses to complain about Wi-Fi. Dense circumstellar material can be especially revealing. For a massive star to have dense gas close around it at the time of explosion, it may have lost mass shortly before death. This could happen through strong stellar winds, eruptions, binary stripping, or unstable late burning stages inside the star. Some theories suggest that in the final phases before core collapse, waves generated deep inside a massive star could deposit energy in the outer layers and drive mass loss. Others point to binary interaction, where a companion star pulls material away or causes common envelope evolution. If FBOT radio emission really indicates dense nearby gas, then these events may be telling us about what massive stars do right before they die, a period that is extremely difficult to observe directly. This is one reason the radio clues refuse to behave. They do not only describe the explosion, they also describe the star's past. A bright radio afterglow may mean the explosion was energetic, but it may also mean the star prepared a dense environment for the shock. If two events have similar explosions but different surroundings, their radio signals may differ. If two stars shed material in different patterns, perhaps a disk around the equator or a wind in all directions, the radio light can change depending on our viewing angle. The same central engine might produce different radio behavior if the surrounding gas is clumpy, asymmetric, or shaped by a companion, so even when radio waves provide clues, they do not always provide simple clues. They are honest, but they are not always tidy. X-rays are similarly difficult. If they come from a central engine, then what kind? A black hole feeding on fallback material? A neutron star spinning down? A Magnetar wind nebula trapped inside the ejector? A shock breakout continuing through dense material? Some models can reproduce parts of the X-ray luminosity but not the rapid variability. Others can explain the variability but struggle with the optical light. Still others can fit one event but not the next. That is why the phrase clues that refuse to behave fits so well. The observations are not vague. In many cases they are precise and valuable. The problem is that they point toward complex physics, perhaps more than one kind of origin, and a class of events that may be less like a single species and more like a small ecosystem. There is also the matter of absorption. X-rays can be blocked or softened by material around the source. Radio waves can be absorbed by dense plasma through processes like synchrotron self-absorption or free absorption. Optical light can be scattered or reprocessed. What we see is therefore shaped not only by what is emitted, but by what the emission has to travel through. In an FBOT, the surrounding debris is expanding and thinning rapidly. A central engine that is hidden on day one might become visible later. Radio waves at one frequency might be absorbed early, but emerge at higher frequencies. X-rays might escape through a low-density path or be reprocessed into optical light. The explosion is not a static lamp. It is a changing fog around a changing source. This helps explain why follow-up has to be rapid and long-lasting at the same time. Rapid, because the early optical and X-ray behavior can change in hours or days. Long-lasting, because radio emission and late X-rays may reveal the engine or shock evolution over weeks, months, or even longer. An FBOT can fade from optical view quickly and still remain scientifically alive in invisible wavelengths. The blue light may be the moment that gets the headline, but the radio and X-rays keep the investigation going after the visible show is dimmed. For astronomers, that means the discovery is not the end of the work. It is the beginning of a long chase across the spectrum. There is something very human about that chase. Telescopes designed for different kinds of light must work together. Optical surveys find the transient. Swift or other space telescopes may catch ultraviolet and X-rays. Chandra or XMM Newton may study high-energy details. Radio arrays like the Very Large Array, a TCA, Meerkat, or millimeter facilities may trace the shock. Each instrument adds a piece that the others cannot see. No single telescope owns the whole truth. It is a cooperative act across wavelengths, time zones, observatories, and teams, all because a distant object briefly misbehaved in blue light. And yet, even with all this effort, the clues remain difficult. The cow's X-rays suggest an embedded compact source. The camel's radio suggests a fast shock in a dense environment, while its X-rays likely require a separate component. A T2O2OM F's X-rays are so luminous and persistent that a central engine becomes hard to avoid. The koala's radio points to energetic outflows. Other events add their own variations. Each one supports the idea that FBOTs are engine-driven or strongly interacting explosions. but each one also brings enough differences to keep the models from settling. The universe seems to be saying, yes, you're getting closer, but please do not become too comfortable. For all their difficulty, these wavelengths are precious because they reveal physics that optical light alone cannot. X-rays take us inward, toward compact objects, accretion, and high-energy processes. Radio waves take us outward, toward shocks, outflows, and the material surrounding the star. Together, they let astronomers map the event from the inside out. The optical flash is the visible skin. The X-rays are the heartbeat or engine noise. The radio is the sound of the blast meeting the room around it, though not sound in the literal sense because space remains stubbornly silent. If we want to know what FBOTs are, we need all three. A simple fading explosion would be easier. It would rise, peak, cool, and decline according to a recognizable pattern. The spectra would classify it. The radio would be modest or predictable. The X-rays would be weak or clearly shock-powered. The model would settle into place. FBOTs do not do that. Their invisible signals keep reopening the case. A radio curve points to dense circumstellar matter. An X-ray flare points to compact activity. A high-frequency signal hints at a neutron star or black hole. A late detection says the engine may still be alive. A mismatch between radio and X-ray components says one mechanism is not enough. Every time scientists try to close one door, another wavelength knocks from the other side. That is why these clues are so exciting. They may be messy, but they are not useless. They are exactly the kind of mess that means something interesting is happening. If FBOTs were smooth and predictable, they would already be filed away. Instead, they sit at the crossroads of stellar death, compact object birth, mass loss, accretion, shocks, and high-energy radiation. X-rays and radio waves do not merely decorate the mystery, they define it. They are the reason astronomers suspect that hidden engines are present. They are the reason FBOTs may connect ordinary supernovae to rarer, more extreme explosions. They are the reason the cow, the camel, the koala, and their strange relatives are not just fast blue flashes, but possible windows into the most secretive moments of collapse. By this point in the trail of blue light, the mystery has become less like asking whether something exploded, and more like asking what kind of hidden machine could make an explosion look this strange. The visible flash has already told us that fast blue optical transients are hot, quick, and luminous. The radio waves have already suggested that fast material is ploughing into gas around the source. The X-rays have already whispered that something compact and energetic may still be active inside the debris, so now the question becomes sharper and also more difficult. Are we looking at a failed supernova, where a star tried to explode but collapsed into a black hole while some of its material fell back? Are we seeing a hungry black hole feeding on a star, on stellar debris, or on the remains of a collapse? Or are we watching the birth of a magnetar, a newborn neutron star spinning rapidly with a magnetic field so powerful that it can pump energy into the wreckage around it? These are not small differences. Each explanation tells a different story about what happened before the flash, what survived after it, and what kind of object was sitting at the center while telescopes on Earth gathered the light. A failed supernova is a story about a massive star reaching the end of its life and losing the battle with gravity in a way that does not produce a normal clean explosion. A black hole feeding event is a story about matter falling into one of the most efficient engines nature allows, releasing energy as it spirals inward. A newborn magnetar is a story about a neutron star so magnetic and so fast spinning that its own birth may light up the debris of its parent star. All three can sound plausible, all three can sound dramatic, and, inconveniently, all three can explain some of the clues while struggling with others. That is why FBOTs have not settled into one simple category. If the evidence pointed cleanly toward one explanation, the mystery would be much easier to narrate. We could say, there it is. A star collapsed, a black hole formed, and the blue flash was the result. Then gently close the notebook and go make tea. but the universe does not seem interested in being that tidy. The observations overlap. Some features resemble unusual supernovae, some resemble accreting compact objects, some resemble engine-powered explosions, some resemble tidal disruption events, where a star is torn apart by a black hole. The result is a scientific crossroads where several paths look promising, and each one has a warning sign that says, "Careful, this gets complicated." Let us begin with the failed supernova idea, because it sits closest to the familiar picture of massive star death. In a normal core collapse supernova, a massive star exhausts its nuclear fuel. Its core can no longer support itself. Gravity crushes the inner region inward, and under the right conditions a shock launches outward, blasting the star's outer layers into space. The explosion shines, the debris expands, a neutron star or black hole may remain at the centre. This is already an enormous process, but it has a recognisable shape. A failed supernova or partly failed explosion changes the outcome. The star collapses, but the explosion may be weak, incomplete, or oddly structured. Some material escapes, some material falls back. A black hole may form and begin feeding almost immediately. Instead of one clean outward blast, the event becomes a struggle between escape and collapse. That struggle could help explain why an FBOT is so fast. If only a relatively small amount of material is ejected, then light can escape more quickly. A large heavy envelope would trap radiation, slowing the rise and broadening the light curve. But low-mass ejecta can become transparent sooner. If a central engine is also adding energy, the event can become both fast and bright, which is exactly the awkward combination that makes FBOTs so hard to explain. The failed supernova picture says, in effect, that we may be seeing a massive star's collapse, with unusually little debris blocking the view. The star did not throw out a huge thick shell in the usual way. The curtain was thinner, or torn, or arranged unevenly, allowing us to glimpse the inner activity before it would normally be hidden. This could also connect to the X-rays. If a black hole forms and fallback material spirals into it, X-rays can be produced near the compact object. Those X-rays might escape through gaps or be reprocessed by surrounding material into optical and ultraviolet light. The visible blue flash could therefore be the outward face of a deeper collapse. The radio waves could come from fast ejecta hitting gas the star had shed before death. In this picture, the FBOT is not one process, but several happening together. Collapse, partial explosion, fallback, accretion, shock interaction, and radiation escaping through an unusually open structure. It is less like a firecracker, and more like a building coming apart while the generator in the basement switches on. But failed supernova models have their own burdens. They must explain why the star lost so much of its outer mass before death, or why the ejecta mass is low enough for the light to rise quickly. They must explain why the central engine is visible so early. They must explain the high temperatures, the luminosity, the radio behaviour and the host environments. A failed supernova from a blue supergiant or a stripped massive star can be made to fit some of the data, especially if the star was surrounded by dense material and the explosion was asymmetric. But every extra ingredient needs a reason. The star must have the right mass, the right structure, the right surroundings, the right collapse, and the right viewing angle. That is possible, but it is not simple. It is astronomy's version of saying, this recipe works, provided the oven is tilted, the cake pan is magnetic, and the flour was ejected 3 months ago. The hungry black hole idea overlaps with the failed supernova idea, but it can also mean something different. A black hole may be born in the collapse of a massive star, or it may already exist and tear apart another star. In either case, the key word is accretion. A black hole with matter around it can release tremendous energy from the gas that falls inward. The black hole itself remains dark, but the surrounding flow can become bright, hot, and violent. Gas spiraling inward can form a disk. The inner disk can radiate X-rays. Magnetic fields can help launch winds or jets. If the accretion rate is extremely high, the system can become thick, unstable, and luminous, producing radiation that may be absorbed and re-emitted by surrounding debris. This is attractive for FBOTs because accretion can be powerful and compact. It naturally explains why X-rays might be bright and variable. It gives a reason for continuing energy after the initial flash. It can produce outflows that help explain radio emission. And it can operate on short timescales if the material is close to the black hole. In the cow, for example, some models interpret the central source as an accreting black hole, possibly formed in a stellar collapse or connected to a disruption event. If matter fell inward at a high rate, it could produce the kind of engine needed to power the observed luminosity. The optical blue light may not come directly from the disk itself, but from surrounding material that absorbs the engine's high-energy radiation and re-emits it at longer wavelengths. In simple terms, the black hole heats the room, and the room glows blue. A tidal disruption scenario gives the hungry black hole a different meal. In a tidal disruption event, a star passes too close to a black hole. Gravity pulls harder on the near side of the star than on the far side, stretching it until it is torn apart. Some material escapes into space, some remains bound and falls back toward the black hole. As it accretes, it shines. This explanation is well established for some events near the centers of galaxies, where supermassive black holes live. But FBOTs complicate the tidal disruption picture because some of them occur away from galactic centers or in environments that look more like massive star regions. That does not rule out all tidal disruption models. A smaller intermediate mass black hole could exist outside a galaxy's nucleus, perhaps in a star cluster or dwarf galaxy environment. A white dwarf could be torn apart by such a black hole. A compact system could create a flare with FBOT-like behavior. But the setting has to cooperate. The Finch made this idea more interesting because of its strange location far from obvious host galaxy centers. If an LFBOT occurs far out in the outskirts or between galaxies, then a massive star death becomes harder to explain unless there is a hidden faint host, a runaway star, or some other special path. A black hole disruption in a globular cluster or faint satellite system becomes more tempting. But other events, like the cow, koala, and camel, appear more connected to star-forming galaxies, which leans back toward massive star origins. This is why one explanation may not cover the whole family. Some FBOTs may be dying stars, some may be disruptions by black holes, some may be mergers or rare compact systems. They may share a fast blue appearance because each one creates a small, hot, luminous region for a short time, even if the underlying cause differs. The hungry black hole also has to explain the radio environment. If the event is a tidal disruption in a relatively clean region, where does the dense surrounding material come from? If the radio emission implies a shock moving through gas shaped by a massive star's wind, that favours stellar death. If the event is offset from a galaxy and still radio bright, perhaps the surrounding material comes from the disrupted star itself, or from a dense cluster environment, or from an outflow launched by accretion. Each possibility can be made plausible in some cases, but the details matter. A black hole can eat many things in theory. The question is what it was eating, where, and why the meal looks so blue from 200 million light-years away. Then there is the newborn magnator. This explanation is elegant in a different way. A magnator is a neutron star with an extremely strong magnetic field. A neutron star is already extraordinary. A collapsed stellar core squeezed into a sphere about the size of a city, with more mass than the Sun packed into matter so dense that ordinary language begins to creak. If that neutron star is born spinning rapidly, with a rotation period of only a few milliseconds, it contains an enormous amount of rotational energy. If it has a powerful magnetic field, that energy can be transferred into the surrounding ejector as the star spins down. The magnetar becomes a central engine, not by feeding on material like a black hole, but by losing its own spin energy into the debris. This can naturally make an explosion brighter than radioactive decay alone would allow. The magnetar injects energy from the inside, heating the ejector and possibly producing high-energy radiation. In some models of AT2018 cow, a millisecond magnetars with a strong magnetic field can reproduce parts of the optical and X-ray behaviour. The magnetar wind can dissipate energy inside the ejector, and some high-energy photons can leak out while others are absorbed and re-emitted as optical or ultraviolet light. This creates a layered system, an inner magnetar wind, an expanding shell, and escaping radiation. The blue light is not simply the cooled surface of the explosion, it is the outer expression of a magnetic engine. The magnetar model has a comforting feature. It keeps the event firmly connected to massive star death. A massive star collapses, leaves behind a neutron star, and that neutron star powers the transient. The host galaxies of some cow-like events, with active star formation, fit that story reasonably well. The fast timescale can be helped by low ejector mass. The high temperature can be maintained by energy injection. The X-rays can come from leakage or emission associated with the magnetar wind. The radio can arise as the ejector or engine-driven outflow runs into circumstellar material. It is a coherent picture, and coherent pictures are attractive when the data are unruly. But magnetars too have difficulties. The ejector mass, velocity, magnetic field strength, initial spin period, opacity and geometry must all line up. If the ejector is too massive, the light escapes too slowly. If it is too thin, too much high-energy radiation may leak out or fail to thermalize. If the magnetar injects energy too quickly, it may produce signatures that do not match the observations. If it injects energy too slowly, it may not explain the rapid rise. And if a compact X-ray rhythm is interpreted as a spin signal, the inferred neutron star properties must make physical sense. Like the black hole model, the magnetar model can explain many clues, but it has to be tuned carefully. Nature may indeed tune things carefully, but scientists become suspicious when a model requires every knob to be set just so. There is another subtle problem. A magnetar and a black hole can sometimes imitate each other from a distance. Both can provide a compact central engine. Both can produce high-energy radiation. Both can inject energy into surrounding material. Both can drive outflows. If you cannot directly see the central object, you must infer its identity from timing, spectra, luminosity, energy budget, and how the light changes across wavelengths. That is a difficult task. It is like hearing noises from behind a wall and trying to decide whether someone is using a blender, a drill, or an angry vacuum cleaner. The sounds may overlap. The wall may muffle the details, and in the FBOT case, the wall is made of expanding stellar debris moving at thousands of kilometers per second, which is very inconsiderate of it. This is why the X-ray quasi-periodic signal reported in the cow is so intriguing. A rapid signal suggests a compact object. It narrows the scale of the source. But it does not automatically tell us whether that compact object is a neutron star or a black hole. If it were a neutron star spin signal, that would point strongly toward a newborn neutron star or magnetar. If it came from orbital or disk processes near a black hole, it could support accretion. The same clue can be read in more than one way, depending on the model. It is valuable, but not final. A good clue can open a door without telling you what room you're entering. There are also hybrid ideas, because the universe is rarely considerate enough to choose one category. A massive star might collapse into a black hole after briefly forming a neutron star. A magnetar might power early emission before collapsing later into a black hole. A black hole might form inside a star during a failed explosion and launch outflows that interact with material the star shed earlier. A compact object companion might spiral into a massive star, depositing energy and helping create a strange explosion. A star might be torn apart by an intermediate mass black hole in an environment that also contains dense gas. These hybrid models are harder to explain in one sentence, but they may be closer to what nature actually does. Real stars rotate, orbit companions, lose mass, erupt, merge, and die in environments shaped by earlier episodes. The clean categories may be ours, not the universe's. The phrase failed supernova can also be misleading if taken too literally. Failed does not mean nothing happens. It does not mean the star quietly vanishes, leaving only a polite note. A failed or partially failed explosion can still produce light, eject material, form shocks, and create a transient. The failure refers to the explosion not fully unbinding the star in the normal way, or to much of the material falling back onto the central remnant. In fact, that fallback may be exactly what powers the event. Failure, in this case, may be the engine's opportunity. Gravity wins enough to form a black hole, but not so completely that we see nothing. Some material escapes, some falls back. The result is neither a normal supernova nor a silent collapse, but a luminous, fast, strange event that briefly shows us the boundary between the two. That boundary is scientifically important. Astronomers want to know which massive stars become neutron stars and which become black holes. They want to know how often black holes form with bright explosions and how often they form quietly. They want to know whether some failed supernovae can be seen as fast blue transients. They want to understand how stellar mass, metallicity, rotation, binarity, and late-stage mass loss affect the final outcome. FBOTs may be rare signposts of this transition. If the cow was a compact object being born in real time, then it was not just an odd explosion. It was a glimpse of one of the universe's most important handoffs, a star becoming a remnant. The black hole feeding scenario touches another major question: where intermediate mass black holes live and how they reveal themselves. Stellar mass black holes are formed from collapsed stars. Supermassive black holes sit in the centers of galaxies. Intermediate mass black holes, with masses between those categories, are harder to find. If some FBOTs are caused by intermediate mass black holes disrupting stars, then these flashes could become a way to locate hidden black holes in dwarf galaxies, star clusters, or galactic outskirts. That would make FBOTs important for black hole demographics, not just stellar death. A brief blue flash could point to a dark object that would otherwise remain unseen. The explosion becomes a signpost saying, something compact and massive lives here, although again, the signpost only appears briefly and then fades, because apparently even cosmic signposts enjoy being difficult. The magnetar scenario connects FBOTs to another family of cosmic events, superluminous supernovae and possibly some gamma-ray bursts. Rapidly spinning magnetars have been proposed as engines for exceptionally bright supernovae. Magnetars are also linked to high-energy phenomena, flares, and extreme magnetic physics. If FBOTs are powered by newborn magnetars, they may reveal a lower-mass, faster-evolving version of magnetar-driven explosions. They might show what happens when the ejector is thin enough for energy to escape quickly, or when the geometry allows high-energy photons to leak. This would place them within a broader landscape of engine-driven stellar deaths, from ordinary supernova to superluminous events to gamma-ray bursts. The cow and its relatives would not be isolated oddities. They would be a bright, quick corner of a much larger map. So how do astronomers decide between these explanations? They gather more light. That sounds simple, but it means many things. They need early optical spectra to see whether hydrogen, helium, or other elements appear. They need ultraviolet observations to measure the hot early emission. They need X-rays to search for compact engines, variability, and late-time activity. They need radio and millimeter data to measure outflows and circumstellar density. They need host galaxy studies to learn whether the event happened in a young star-forming environment, an old stellar population, a dwarf galaxy, a globular cluster, or a faint hidden system. They need late-time imaging, sometimes years later, to see what remains after the transient fades. They need larger samples because one event can be misleading, and two events can still be mischievous. They also need theory. Observations provide the clues, but models test whether a proposed engine can actually produce them. A model must ask how much mass was ejected, how fast it moved, how opaque it was, how much energy the engine released, how quickly that energy escaped, what surrounding material was present, and what the event would look like from different viewing angles. It must reproduce the optical light curve, the color evolution, the spectra, the X-rays, the radio waves, and the timing. This is not easy. A model that fits the optical light may fail in X-rays. A model that fits the X-rays may overpredict radio emission. A model that fits the early days may fail at late times. The data are a strict audience, and they do not clap politely. For now, the honest answer is that no single explanation has won for every FBOT. The cow may have involved a compact object revealed unusually early. The camel and koala support engine-driven or shock-interacting pictures with fast outflows. The finch keeps open the possibility of different environments and perhaps different progenitors. The Tasmanian devil's repeated flares, which wait just ahead in our journey, make simple fading models even harder. Failed supernovae, accreting black holes, and newborn magnetaires remain the main suspects because each one can provide the required energy in a compact form. But none of them gets to leave the interrogation room just yet. There is a quiet beauty in that uncertainty. Science is sometimes presented as a list of answers, but much of it is really a disciplined way of living with unanswered questions. Not vague questions, but sharpened ones. Not, what was that, in a broad sense, but can a low-mass ejector model with a central magnetar reproduce the X-ray leakage and optical rise time? Or can fallback accretion onto a newly formed black hole power the luminosity while matching the radio-inferred density? Or could an intermediate mass black hole tidal disruption event occur in this environment and produce this timescale? These are not sleepy questions for the scientists asking them, perhaps, but they are part of the same calm human effort to understand what the universe is doing when it briefly glows blue and then refuses to explain itself. For us, drifting through the story more gently, the three suspects give us a way to hold the mystery. A failed supernova says the star's death was incomplete, messy, and partly swallowed by gravity. A hungry black hole says matter fell inward and released enormous energy as it fed a compact darkness. A newborn magnetar says a dense magnetic remnant spun so fiercely that it lit the debris from within. Each is extreme, each is plausible in some form, each turns the FBOT from a simple flash into a doorway. Behind the doorway is not just light but collapse, accretion, magnetic fields, fallback, shocks, and the birth of objects that can reshape their surroundings long after the original star is gone. And maybe that is why these events feel so important. They sit at the moment when a star stops being a star and becomes something else. They may show us the transition between ordinary matter and compact remnants, between explosion and collapse, between visible death and hidden survival. Whether the engine is a black hole feeding on fallback gas, a magnetar spinning down inside the debris, or a failed supernova struggling to eject its outer layers, FBOTs are telling us that some stellar deaths are not clean endings. They are active, uneven, engine-driven transformations. The blue light is the signal flare. The real story is happening underneath. As more of these events appear in survey data, astronomers will keep testing the suspects. Some FBOTs may point more strongly toward black holes, others may lean toward magnetiars, others may turn out to be failed explosions inside dense shells of material, or tidal disruptions in unexpected places, or mergers that briefly imitate the others. The family may split, the names may multiply, the models may become stranger before they become clearer. By now, the strange blue flash has become more than a flash. It has become a possible doorway into a kind of stellar death that does not fit neatly beside the supernovae astronomers already know. That is a strong thing to say because supernovae themselves are not simple. They are not little pops in the dark, not tidy endings, not the sort of event you would casually file away between star got tired and space did something bright. A supernova is already one of nature's great acts of transformation. A massive star collapses, a shock wave moves outward, elements are forged and scattered, and the remains of the star may become a neutron star or black hole. It is violent, useful, beautiful, and deeply complicated. Yet fast blue optical transients seem to suggest that even this grand story may have hidden branches we are only beginning to notice. The phrase, new kind of cosmic death, does not necessarily mean that the universe has invented a brand new law just to confuse astronomers, although it sometimes feels emotionally close to that. It means that FBOTs may reveal a rare pathway by which stars or compact objects end their lives, a pathway that is fast, engine-driven, and unusually exposed. In ordinary stellar death, the central action is often hidden. A massive star collapses deep inside itself, and the outer layers may take time to reveal what has happened. If a neutron star or black hole is born, it can be buried under expanding debris. We may infer its presence later, after the glow fades, or after the remnant begins interacting with its surroundings. But an FBOT may pull that inner transformation closer to the surface. It may let energy from the central engine escape almost immediately, giving astronomers a brief glimpse of the machinery usually hidden beneath the wreckage. That is what makes the idea so important. If FBOTs are simply odd-looking supernovae, they are still valuable. They teach us about fast explosions, hot material, and unusual mass loss. But if they are a distinct path of compact object birth, then they become something deeper. They become a way to watch a star stop being a star and become a neutron star, magnetar, or black hole, not in the calm language of diagrams, but through the actual light escaping from the event. They may show us what happens when collapse and explosion do not separate cleanly. They may show us stellar death as a struggle, not a switch. Some material escapes outward, some falls inward, some powers shocks, some feeds a compact object, some glows blue for a few days, as if the universe has cracked open the door to an engine room and then closed it again before we can step inside. In many familiar supernova models, the visible light is powered in large part by radioactive decay and by the heat stored in expanding debris. That process is not boring, but it is relatively well understood compared with the rapid, luminous blue behavior of FBOTs. The difficulty with FBOTs is that their properties seem to demand a different arrangement. There may be less ejecta, allowing light to escape quickly. There may be dense gas around the star, allowing shocks to convert motion into radiation. There may be a compact engine injecting energy from within. There may be a symmetry so that radiation escapes through a hole or funnel rather than through a thick spherical blanket. The result is an explosion that looks less like a standard glowing shell and more like an active system in which the centre, the debris and the surrounding material all matter at once. This can reveal a new kind of cosmic death because the final moments of massive stars are still full of uncertainty. Astronomers know the broad outline. Massive stars burn through fuel quickly, build heavier elements in their cores, and eventually collapse when fusion can no longer support them. But the details depend on mass, rotation, metallicity, magnetic fields, and perhaps most importantly, companions. Many massive stars are not alone. They live in binary or multiple systems, orbiting other stars closely enough for gravity to strip material, transfer mass, spin them up, or disturb their final structure. A star that dies alone may look one way. A star that dies after years of being tugged, stripped, or swallowed by a companion may look very different. FBOTs may be a sign that some stellar deaths are shaped by this complicated private life before the collapse. Binary interaction is especially tempting because it can explain why the exploding star might be stripped of much of its outer envelope. If a companion pulls away hydrogen or helium layers, the final star may be more compact and lighter in ejecta. That can make the transient faster. A companion can also help create dense circumstellar material, either through winds, mass transfer, or a common envelope phase where one star spirals inside the outer layers of another. If the final explosion runs into that material, it can produce bright shocks and radio emission. If a compact object is already present in the system, the interaction can become even stranger. A black hole or neutron star might merge with the core or disturb the star before it dies. In that case, the FBOT would not be a normal supernova with a small adjustment. It would be the visible sign of a stellar system ending through a complicated gravitational accident. A black hole and Wolf-Rayet star merger is one of the more dramatic possibilities. A Wolf-Rayet star is a massive star that has lost much of its outer envelope, exposing hot inner layers and driving strong winds into space. If such a star is in a close binary with a black hole, the system can become unstable. The black hole might spiral inward, deposit energy, and eventually merge with the star's core. That could launch an energetic outflow, create a compact engine, and leave behind dense surrounding material. It is not the only possibility, but it shows the kind of pathway FBOTs might reveal. Not just a star exploding, but a star being transformed by a companion and then dying in a way that produces a fast blue flash. Failed supernovae offer another route to a new kind of cosmic death. In a failed or partly failed supernova, the star does not simply explode cleanly and send most of its outer layers into space. Instead, the collapse may form a black hole, and some of the material that first moved outward may fall back. This fallback can feed the black hole and power an accretion engine. In this picture, the FBOT is not a successful supernova in the traditional sense, nor is it a completely dark collapse. It is something in between. Enough material escapes to shine. Enough material falls back to feed a central engine. Enough of the debris is thin or asymmetric that we can see the energy quickly. That in-between state is scientifically precious, because astronomers still want to know how often massive stars form black holes quietly, and how often they do so with a visible explosion. If FBOTs mark that boundary, they could help answer a major question in stellar evolution. Which stars explode, and which stars disappear? This sounds simple, but it is not. The most massive stars might be expected to produce the biggest explosions, yet some theories suggest that very massive cores may collapse directly into black holes with little visible display. Observers have even searched for massive stars that vanish rather than explode brightly. FBOTs may represent another possibility. Not a normal supernova, not a silent disappearance, but a short, hot, engine-powered flare from the messy moment when collapse partly wins and partly loses. A star can die, a black hole can form, and the universe can still briefly flash blue. A newborn magnetar tells a different version of cosmic death. Here the star's core does not collapse all the way into a black hole. It stops as a neutron star, but not a quiet one. It is born spinning rapidly, with a magnetic field so intense that it can reshape the debris around it. The magnetar loses rotational energy and pumps that energy into the expanding material. This can make the transient brighter and hotter than radioactive decay alone. If the ejecta mass is low enough, the light can escape quickly. If some high-energy radiation leaks out, it can explain X-rays. If the magnetar wind drives shocks, it can contribute to radio emission. In this view, the FBOT is the first announcement of an extreme compact object, a newly born magnetic remnant shining through the remains of its parent star. That possibility is fascinating because magnetars are themselves mysterious. We know they exist in our galaxy, usually seen through bursts of high-energy radiation and unusual neutron star behavior. But watching one being born is much harder. If FBOTs are linked to newborn magnetars, then they may let us study the earlier stage of an object that later becomes a strange compact remnant. The blue light would be a kind of birth cry, not of a living creature, of course, but of an object so dense, fast, and magnetic that it turns the death of a star into a luminous signal across millions of light years. Tidal disruption events complicate the phrase cosmic death in another way. In a tidal disruption event, the star may not die because it exhausted its fuel. It dies because it came too close to a black hole. Gravity tears it apart. Some material falls inward and shines. Some is flung away. Most known tidal disruption events occur near supermassive black holes at the centres of galaxies. But some FBOTs, especially those in unusual locations, keep open the possibility of smaller or intermediate mass black holes disrupting stars outside galactic nuclei. If that happens, an FBOT could reveal not the death of a massive star by collapse, but the death of a star by encounter. A star wanders too close to hidden darkness, and for a few days the universe lights up in blue. That would also be a new kind of signpost. Intermediate mass black holes are hard to find. They are too small to dominate a bright galactic centre like a supermassive black hole, but too large to be ordinary stellar remnants. If some FBOTs are produced when such black holes tear apart stars, then these flashes could help locate hidden black holes in dwarf galaxies, star clusters, or galactic outskirts. The transient would become evidence for an otherwise invisible object. It would be as if the black hole briefly turned on a lamp by destroying something that passed too close, which is not polite behaviour, but it is useful for astronomy. The Finch made this part of the story especially intriguing. Its location far from obvious galactic centres challenged the idea that every luminous FBOT comes from a young massive star in a star-forming region. That does not rule out massive star models, because hidden dwarf galaxies, runaway stars, or diffuse young environments can complicate the picture. But it does widen the range of possibilities. A new kind of cosmic death may not even be one kind. The FBOT label may contain several rare endings that share a similar visible appearance. Some may be failed supernovae, some may be magnetar births, some may be black hole disruptions, some may be mergers. The universe may have built several different roads that all pass briefly through the same blue gate. This is not unusual in astronomy. Early classifications often group objects by how they look. Later, scientists discover that the physical causes are more diverse. Long ago, many fuzzy objects were called nebulae, before astronomers realized some were nearby gas clouds and others were entire galaxies. Gamma-ray bursts were once a single mystery before being divided into long and short classes with different origins. Supernovae themselves come in many types, powered by different mechanisms and produced by different progenitors. FBOTs may be at a similar stage. We are seeing the visible behaviour first. The deeper physical classification is still forming. Even so, the shared behaviour matters. Fast, blue, luminous, and often loud in X-rays or radio. Those traits suggest compactness, heat, energy, and motion. They suggest that something about these deaths allows energy to escape quickly. They suggest that some stars or stellar systems end with less debris, more central power, stronger interaction, or more extreme geometry than ordinary supernova. They may reveal a narrow phase of astrophysics that was always there but easy to miss before modern surveys. The events are brief, so older observing strategies might have skipped over them. Only now, with wide-field surveys scanning the sky night after night, are we beginning to catch them before they fade. In that sense, FBOTs could reveal a new kind of cosmic death, not because the universe recently began making them, but because we recently became fast enough to notice. The sky has always been changing, stars have always exploded, black holes have always fed, compact remnants have always formed. But human astronomy spent much of its history looking at a sky that seemed mostly still. Now we watch repeatedly, automatically, across wide fields, comparing one night with the next. We have taught telescopes to notice when the universe blinks, and when it blinks blue, fast and bright. We now know that the blink may be telling us about an ending we used to miss. There is also a deeper connection to the life cycle of matter. Stellar death is not only destruction, it is how the universe changes its ingredients. Supernovae spread heavy elements. Neutron star mergers make some of the heaviest elements. Black holes reshape gas and galaxies through accretion and jets. If FBOTs represent a rare kind of stellar death, they may also play a role in distributing material, forming compact objects, and shaping their local environments. They may not dominate the universe by number, but rare events can still matter. A single kind of explosion can teach us about conditions that are otherwise hidden. A rare death can reveal a common question. For the stars involved, if they are stars, the ending may be brief from our point of view, but long in preparation. A massive star may spend millions of years building its core, losing mass, interacting with a companion, changing its rotation, and shaping the gas around it. Then, in a few days of observed blue light, the final result is revealed. That contrast is astonishing. A life measured in millions of years becomes a flash measured in human nights. A star's hidden history becomes a transient alert. The final signal races across space for hundreds of millions of years and lands in a telescope database, where someone notices that it is too fast, too blue, and too strange to ignore. That is why FBOTs are so powerful as scientific clues. They compress a long story into a short display. They may show us not just how stars die, but how the final conditions before death determine the outcome. Was the star stripped? Did it have a companion? Did it form a magnetar? Did it collapse into a black hole? Did material fall back? Did the explosion hit a dense shell? Was there a jet? Was the whole system viewed from a special angle? These questions are all packed into the light curve, spectra, X-rays, radio emission, and host environment. The event fades quickly, but the information it carries spreads across years of research. So, when we say FBOTs could reveal a new kind of cosmic death, we are really saying they may reveal one of the missing transitions in the life of massive stars and compact objects. Not the calm main sequence, not the familiar red giant swelling, not the classic supernova alone, but the messy boundary where collapse, explosion, accretion, magnetism, mass loss, and companionship all meet. A place where the difference between neutron star and black hole, between explosion and failure, between star death and compact object birth, may be written in a few days of blue light. And so we arrive with the blue light still fading, not fully gone, not fully understood, and perhaps that is the most honest place to end a journey through Fast Blue Optical Transients. We have followed the strange flash from its first sudden appearance in survey images, through the cow and its oddly named relatives, into X-rays, radio waves, hidden engines, failed supernova, hungry black holes, newborn magnetars, and possible new pathways of cosmic death. We have watched the mystery become clearer in shape without becoming solved in detail. That happens often in science. A question becomes sharper before it becomes answered. The fog does not lift all at once. Sometimes it thins enough for us to see that the landscape is larger than we thought. Astronomers still cannot explain FBOTs completely, because every explanation leaves something behind. A failed supernova can explain a collapsing massive star fallback, and perhaps a black hole feeding inside low-mass ejector, but it must account for the extreme speed, high temperature, dense surroundings, and visible engine. A newborn magnetar can provide a powerful central source, but it must release energy on the right timescale and through the right amount of debris. A black hole tidal disruption event can explain accretion and high-energy emission, but it must match host locations, radio environments, and the fact that some events seem closely tied to star-forming galaxies. Shock interaction can make bright light and radio waves, but it struggles when X-rays look too compact or too variable. Geometry and viewing angle can help, but they can also make the same event look different from different directions, which is useful and slightly annoying in equal measure. The problem is not that scientists have no ideas, it is that they have too many ideas that work partly. This is a very particular kind of scientific frustration. It is easier when every model fails completely, because then you can sweep the table clean and start over. It is also easier when one model fits everything beautifully, because then everyone can nod, write a tidy review, and argue only about the smaller details. FBOTs sit in the middle. The models are good enough to be tempting and imperfect enough to remain suspicious. They explain some observations while stumbling over others. The cow seems to demand a compact engine. The camel points to fast outflows and dense surroundings. The koala strengthens the radio connection. The finch changes the environmental expectations. The Tasmanian devil adds late repeated flares that make simple one-time explosions look increasingly uncomfortable. Each event says, yes, but also this. This is why the mystery is still fading in blue light. The visible flash goes away quickly, but the scientific afterimage remains. Long after the transient has dimmed beyond ordinary optical detection, the data keep glowing in a different way. Light curves are modelled, spectra are compared, X-ray archives are reanalyzed, radio emission is fitted with shock models, host galaxies are imaged more deeply. Hubble or other telescopes may look later to see whether a faint cluster, dwarf galaxy, or local environment was hiding underneath. Years after the event, astronomers may still be extracting meaning from photons that arrived during a few short nights. The explosion fades, the work does not. One reason these events remain difficult is that the earliest moments are so important and so easy to miss. An FBOT can rise in only a few days. Its colour, temperature, spectra, and high-energy behaviour can change quickly. If it is discovered after peak, some of the best clues are already gone. You cannot rewind the event. You cannot ask the star to explode again, just a little more slowly this time, perhaps with clearer spectral lines and better weather over the observatory. The first hours and days may hold the key to distinguishing shock cooling from central engine heating, dense circumstellar interaction from radioactive diffusion, or magnetar power from accretion. Missing that early window can leave several models alive when one might otherwise have been ruled out. Another reason is distance. Even nearby FBOTs are far away by human standards. The cow was close enough cosmically to study in remarkable detail, but still in another galaxy about 200 million light-years away. Other events are farther. At those distances, the explosion itself cannot be spatially resolved. Astronomers cannot see the engine, the ejector shape, the disk, the jet, or the surrounding gas directly. They infer everything from light. They study brightness, colour, spectra, timing, polarization when available, and emission across wavelengths. This is powerful, but indirect. It is like understanding a machine by listening through a wall, measuring the heat under the door, and occasionally noticing a flash through a keyhole. You can learn a great deal, but you may still argue about what the machine looks like. The small number of well-observed examples makes the problem harder still. Cow-like luminous FBOTs are rare, and not everyone is caught early or followed across the spectrum. A small sample means each object carries a lot of weight. The cow shaped the early discussion because it was bright, nearby, and well studied. The camel and koala added support for a family. The finch showed that locations may vary, but a handful of objects cannot reveal every branch of the class. Some may be true physical relatives, others may be lookalikes, some may come from massive star collapse. Others may come from compact object encounters. The observational label may be gathering multiple causes under one name, and only a larger sample can sort them. This is a common stage in astronomy. First, a strange object is found, then another, then a class is named, then the class becomes messy. That messiness is not a sign of failure. It's a sign that the observations are real enough to challenge the first explanation. Nature has no duty to match our earliest categories. It gives us objects, not filing cabinets. We build the cabinets afterward, sometimes discovering that the drawers are too small, the labels are wrong, and one of the objects has somehow rolled behind the desk. FBOTs may be in exactly that phase. We can describe them, we can compare them, we can propose engines, but the final cabinet is not built yet. Future surveys will help. Wide-field instruments that scan the sky frequently and deeply, will catch more fast transients. The more often we look, the less likely a brief blue flash will slip past unnoticed. Rapid alerts will allow telescopes around the world and in space to respond quickly. Early spectra will become more common. X-ray and radio follow-up can test whether compact engines are present in most events or only some. Late-time imaging can reveal host environments more clearly. As the sample grows, patterns that are now uncertain may become obvious. Perhaps most luminous FBOTs will turn out to prefer young star-forming regions after all. Perhaps a subset will be found in galactic outskirts, pointing to black holes, clusters, or runaway systems. Perhaps the class will split into several branches, each with its own physical cause. The Vera C. Rubin Observatory, along with other modern surveys, may be especially important because it will repeatedly image huge areas of sky. It will find enormous numbers of transients, including rare and fast events. That will create a new challenge. Discovery may become easier than follow-up. If the sky begins sending too many alerts, astronomers will have to decide quickly which events deserve scarce telescope time. Machine learning systems may help classify candidates early. Networks of telescopes may respond automatically. The future of FBOT science may depend not only on having sharper eyes, but on having faster reflexes. The universe blinks, and we must decide whether the blink is an ordinary supernova, a strange flare, a tidal disruption, or the next cow-like explosion before it fades. Better theory will matter just as much. As more events are found, models must become more realistic. Spherical explosions may not be enough. Researchers will need to explore asymmetric ejecta, jets, disks, dense shells, binary systems, viewing angles, and radiation leaking through changing debris. They will need to simulate how a newborn magnetar's energy moves through low-mass ejecta, how fallback accretion powers X-rays, how a black hole and massive star merger might appear, how circumstellar material shapes radio light curves, and how the same engine might look different from another angle. The goal is not only to fit one event after the fact, but to predict what future events should look like. Prediction is how a model proves it is more than a good story. There may also be clues in neutrinos or gravitational waves, though detecting them from distant FBOTs would be extremely difficult. If some FBOTs involve compact object mergers, black hole formation, or asymmetric collapse, gravitational waves could in principle carry information from the deepest parts of the event. If core collapse is involved, neutrinos could reveal the inner physics, though only for events much closer than most known FBOTs. For now, light remains the main messenger. But astronomy is increasingly a multi-messenger science, and one day a nearby fast blue transient might arrive with more than photons. That would be a very different kind of night for astronomers, and probably not a restful one. For all the uncertainty, FBOTs have already taught us something important. They have shown that the universe still hides fast pathways of energy release that were easy to miss before modern surveys. They have shown that stellar death can be more exposed, more engine-driven, and more diverse than simple categories suggest. They have shown that blue light can be a warning sign, not just of heat, but of hidden compact activity. They have shown that radio waves and X-rays can keep telling a story after the optical glow fades. And they have reminded us that names can be wonderfully misleading. The cow, the koala, the camel, the finch, the Tasmanian devil. Soft names for violent endings, gentle handles on extreme physics. Maybe that contrast is part of why the mystery lingers in the mind. A cosmic explosion named the cow sounds almost friendly, and yet it may mark the formation of a black hole or neutron star. The finch sounds delicate, and yet it may point to an explosion far from where astronomers expected one to be. The Tasmanian devil sounds playful, and yet its repeated flares challenge simple ideas about how explosions fade. The names make the objects easier to remember, but the physics behind them remain severe. Matter collapses, gravity tightens, magnetic fields twist, gas shocks, radiation escapes. a star or system reaches an ending, and for a few days it glows blue enough for us to notice from across the universe. There is a comfort in the fact that we do notice. Humans are small, brief creatures on a small notice planet around an ordinary star, and yet we've built instruments that can catch a sudden flash in another galaxy and ask what happened inside it. We can measure X-rays from a compact engine we cannot see. We can model radio waves from material moving at a fraction of light speed. We can compare a transient in Hercules with another in a dwarf galaxy, another far from its host, another that flares again and again after it should have quieted down. We can take a brief disturbance in the sky and turn it into a question about how stars die, how black holes are born, and how the universe changes its own matter. That is what makes FBOTs a fitting mystery for a quiet night. They are violent, but they reach us gently as light. They are brief, but they open long questions. They are rare, but they may reveal an important hidden path. They are confusing, but not hopelessly confusing. Every new observation narrows the possibilities. Every new event tests the models. Every strange detail, even the ones that refuse to behave, helps shape the next question. Science does not always move by sudden answers. Sometimes it moves by learning exactly why the old answers are not enough. So if you're still awake somewhere under the same turning sky, perhaps with the room a little darker now and the world outside a little quieter, imagine one last time that blue flash appearing in a distant galaxy. For millions of years its light crosses emptiness. It passes between galaxies, through dark stretches where almost nothing interrupts it. On Earth, continents shift, species rise and vanish, oceans change, and eventually a species appears that can build telescopes, computers, satellites, and very strong opinions about how many alarms to set in the morning. Then the light arrives. A survey notices a new point. Astronomers turn their instruments toward it. The point brightens, fades, flickers in X-rays, murmurs in radio waves, and leaves behind more questions than it answered. And maybe that is all right. Not every mystery has to close before the night ends. Some mysteries are better left as open doors, gently lit from the other side. FBOTs are still fading in blue light, still caught between supernova and compact engine, between black hole and magnetar, between known categories and whatever waits just beyond them. Astronomers will keep watching. New surveys will keep scanning. Somewhere in some galaxy, another fast blue flash will appear, and the alerts will go out again. Perhaps that next one will be the clue that settles the matter. Perhaps it will make everything stranger. Either way, the universe will have spoken for a moment, and we will listen. If this strange little journey through cosmic explosions has brought you a bit of calm, or helped your thoughts drift away from the busy edges of the day, I would be very grateful if you liked the video, subscribed, and shared this quiet corner of science with someone else who might enjoy falling asleep under distant mysteries. We began with a blue flash that should not fade so fast, and we ended with a mystery that still refuses to disappear. Somewhere beyond our sky, stars are changing, collapsing, merging, feeding hidden engines, and sending their light into the dark. Here on Earth for now you can simply rest. Sleep well, fellow traveller, wherever you are and wherever the next strange blue light is already on its way from.